Welcome to everybody. So I just I'm Valentino Magnani, one of the organizers. I want to also thank the financial support of many organizations, the Centro De Giorgi, also the Department of Excellence Project of our department, and also the National Project Print, that are the source of funds that make possible this activity. Also, I want to thank the staff of Centro De Giorgi for the important support we had to organize such school. We hope that you will be able to benefit of the courses of the school. So welcome, and we hope that you are able to enjoy the courses. So thank you, and I'm glad to introduce Professor Francesco Maggi from Texas Austin University that will start the lectures on the Plateau problem for wet films. Thank you.
Thanks to Valentino, to Andrea, Emanuele, Giovanni for the invitation to give this course. So this is going to be a lot because apparently it's 4 lectures of 90 minutes, right? Yeah. So it's like this is going to be intense. And so the title of this course is The Plateau Problem for Wet Films. And it's going to be based on, the most recent work is with Michael Novak and Daniel Restrepo. Michael has been a postdoc with me at UT Austin, and then we have kept working on these problems. Recently now he's an assistant professor at the Illinois Institute of Technology. Daniel Restrepo has been my graduate student, advised jointly with Caffarelli. Now he's a postdoc at Johns Hopkins. And then, but before that, so this work kind of goes back more than 10 years at this point. And it starts with a paper with Delellis and Giraldin, about which actually I will talk more today. Having all this time, I'm kind of using it. And so what's going to happen today, so lecture 1, so since we're going to talk about the wet Plateau problem, I will start with the dry Plateau problem, okay? Which is the classical Plateau problem. But it's actually called, this is fun. So at the very end of this, not at the very end because we're still working on it, but about 1 year ago in Oberwolfach, I was presenting some of these more recent results, and Felix Otto pointed me to some literature in the physics engineering community about the stability of foams and films. And and in this literature, as I will explain in the talks, they really distinguish between dry soap films and wet soap films. I mean, as mortals or mathematicians, let's say we think about soap films as wet stuff, right? So, but apparently there are dry and wet soap films, just to distinguish the models, okay? So today is about what the engineers call the dry soap films, and so for me it's the dry Plateau problem. So, and I apologize if you are kind of experts in geometric measure theory. I'm really going to do an introduction, okay? Because there are a lot of basic, very, very basic questions at play in the Plateau problem, right? And I think it's fun, if you see it the first time, to see the story from the beginning and understanding why certain things are done in a certain way. So, but let me do it rather than talking about it. Okay, so the modeling of soap films. So soap films, there is one in the picture down there, done in my kitchen, is this thing here with a wire frame. And the basic mechanism at play when you observe a soap film is the surface tension, which is a tangential kind of force. So imagine that this red surface S is just a tiny piece of this soap film, okay? So we model the soap film as a surface, and there are three relevant objects for each little surface I can carve out of this object, right? There is the unit normal to the surface, there is the unit conormal to the surface, and the boundary of the surface. So the boundary of the surface would be this kind of this line, and then at each point, the tangent plane, I have the normal, and then I have a conormal. So the conormal is a direction in the tangent plane to the surface that points out its unit and point outwards, okay, in the tangent plane. So it's normal to the normal. So the conormal is actually a tangent direction to the surface, okay? But along the boundary of the surface is the tangent direction that it's normal to the surface itself. Okay? Makes sense, right? Good. So, and then surface tension is just the lateral pull, right? On each element of the surface, you have these conormals all along the boundary of the surface, and they're just pulling outwards. So, since there is no special direction, it's just a matter of intensity. So the total force, surface tension force, acting on an element of surface S is going to be the integral along your boundary element of the conormal. And then there is a little, the role of this constant sigma, which is super important in the physics literature, is the object you need to measure to understand the properties of your soap film. The role of this constant sigma is, in my equation, is just to make this a force, right? Because the conormal is an adimensional geometric quantity, it has no dimensions. The integral is a line integral, so if I just do the integral over the conormals, I get something which has the dimensions of a length. But a length is not a force. So you need to normalize this thing, and so you multiply by a constant sigma, whose dimensions are Newton over meters. If Newton is your unit for forces and meters is your unit for length, okay? So this is the basic formula for surface tension. So on each element of this piece of surface, there is this integral acting on it, which is perfectly fine as a formula, but is not very practical to do anything, okay? Because it's just this line integral. So, and then the next thing you do, so here it's a little picture, you can imagine this thing being pulled laterally everywhere, and you do the balance of forces. So the total force at equilibrium must be zero. So if you observe a subfilm and it stays in place, the total force on it is zero. Now there are actually, there is another kind of force acting on the film, and it's just the atmospheric pressure on one side of the film, say from above, and the atmospheric pressure from below. So it's a locally, every film, even if you have a Moebius strip of a film, okay, it's not globally orientable, but locally, and we're thinking really about small pieces of the film, a film is something that separates one side from the other side, right? And on each side, there is going to be a bombardment of air particles, okay, wherever your film is sitting in a room, hopefully, okay, and then there is the air coming in and coming out. So in the case of a soap film, what looks like two regions inside and outside, but it's just the same thing because they're in the same room, right? So the atmospheric pressure on one side and the atmospheric pressure on the other side are the same, just opposite direction, so they cancel out. So for a soap film, all you see here is the surface tension effect, right? When you see it, just to explain myself better, when you see a soap bubble, the soap bubble is going to really separate the surrounding space in two regions, okay? And the atmospheric pressure inside the soap bubble and outside is going to be different. That's why it's round rather than being a minimal surface, because there is this mismatch of the pressures, okay? And if you open one of these physics books, they start like this, okay? They explain the balance of forces. So the condition, when you see a minimal surface, what essentially we expect is that zero is going to be the integral of this thing on every boundary, on every element S of the surface. And now the insight of Laplace and Young, 1805, so this is 220 years ago, is that you can rewrite this line integral as a area integral. So you're integrating on the full piece of surface. What you need to integrate there is the mean curvature vector of your element of surface. So what is the mean curvature vector? Geometrically speaking, is this. So you look at the outer unit normal to the surface, you choose one, it doesn't matter which one of the two, and it's a local computation, it doesn't need to be global, okay? So you choose a local choice of the normal nu of S, and you start taking tangential derivatives of this vector field. So you differentiate your vector field along cars, and then you just compute whatever vector you get. And you're always getting a tangential vector, so because it's normal, so when you differentiate it tangentially, you get a tangential vector. So it's a map from the tangent space to the tangent space, and so it has, and it's symmetric, and so you get eigenvalues. And these eigenvalues are the principal curvatures. So the mean curvature is just that k1 plus k2, the sum of the, which is not a mean because I'm not dividing by 2, but that's just more convenient. So the mean curvature is just the sum of the curvatures times the normal that I have used to make my computation. This way it's independent of the normal. So that's why the mean curvature vector is actually, physically speaking, more important than the scalar mean curvature, which is the object that you obtain by taking this guy and do the scalar product with a normal, okay? And this is what mostly mathematicians talk about. But physically, there is an object that you use orientation locally to define, but then it's a physical, so the mean curvature vector is a normal vector which is defined on a Möbius strip. No problem at all. It's just a normal vector field along your Möbius strip. Somewhere it must be zero, right? Because it cannot be non-zero everywhere. Otherwise, you would have oriented the Möbius strip by normalizing this vector. So this is the mean curvature vector. And then what you do, you just divide by the area of S, send your element of surface to 0, and you localize this condition in mean curvature vector equal to 0. So this is the Laplacian law, or the minimal surface equation, if you want to write it as a scalar equation after taking the scalar product with your favorite choice of a norm. Okay? So that's how you derive H equals 0. It's Newton, so H equals 0 is Newton's law at equilibrium. The total forces acting on the film are 0. Then what are these forces? Surface tension, atmospheric pressure. In the case of a soap film hanging from a wireframe, is the atmospheric pressures are there, but they just cancel out. So actually, the atmospheric pressures are there, and they are going to be responsible for the film to eventually burst up. So they're not eternal, okay? After a while, they will just disappear because the bombardment that keeps going on, okay? And other effects. So this is a scalar mean curvature. So this is how Young and Laplace came up with this thing in 1805 with different terminology, completely different notation. Of course, I mean, this is a sort of historical fake here, okay? And then the next important thing for us is Gauss. So Gauss, in 1830, some decades later, he derives the Young-Laplace equation, mean curvature equal to 0, from energy minimization. So, and as we're going to see in a moment, this is more just than deriving just for the sake of doing mathematics, okay? This actually gives you additional physical insights on what this model is good for. So the idea is, what is energy minimization? So what is the energy involved here? Is the area of the surface. So an area is an area, is not an energy. Again, there is a sigma multiplying everything, and then, right, sigma is Newton over meters, area is meters squared, you get Newton times meters, which is energy. So the energy would be sigma times the area, and then we cancel the sigma because, okay, it's just a constant. So it quickly becomes here area minimization. So the idea could be this. So you have a surface, you compute its area, and now you, minimizing property, it means that among all surfaces, say with the boundary, you have less area. In this case, more pragmatically, you can think even to a class of surfaces. Let's say all the diffeomorphic images of our surface that keep its boundary fixed, okay? So I'm saying diffeomorphisms because I'm trying to be Gauss in the 1830s, and I want to start from a surface, do my thing, and then get another surface, okay? I don't want to get something strange. So I just take my surface, I do a diffeomorphism, and then I see another surface, okay? And then I compare the areas, and I always want to have less area. So the idea is showing that this area minimality property implies that the mean curvature is 0, okay? So I don't know if you've ever seen the computation, but this is a school, right? I mean, again, I'm kind of, okay. So if you have never seen the computation, you need to see this computation. Otherwise, it's like you are, you can't really do these things without knowing this basic stuff, okay? So, so the idea, however, how do you do anything like that, right? In the 1830s, you use calculus. You take a derivative of a function of one variable. So I cannot really, so you see, this condition is as nice as it is, but what are the diffeomorphisms I'm going to use, right? I mean, and this is the basic idea of variations. Okay, this is the calculus of variations in the 1830s was already quite developed, and the idea is you're doing a geometric version of that. So you pick a vector field on your surface S. It doesn't need to be a normal vector field. So here I kind of try to make it not look too normal because I don't want it to be normal, okay? The case of normal vector fields is the one that really matters, but let's say, for reasons it become apparent in a moment, it's not necessarily normal. then this vector field is going to be 0 at the boundary, and then I can imagine of creating from one of these vector fields a family of diffeomorphisms by starting from the identity map and then adding a multiple of the vector field with a parameter t, which is small. And of course, if t is small enough with respect to the size of the vector field I've chosen, these will be diffeomorphisms of my surfaces into R3, okay? Simply because for t small enough, that's a super important exercise to do the first time you see these things, okay? For t small enough, you're not going to lose global injectivity, and for t small enough, the determinant of that map, of the gradient of that map, is going to be the perturbation of the determinant of the perturbation of the identity. So if t is small enough with respect to the C1 norm of the this vector field X, the determinant stays positive, and so you got a proper diffeomorphism, okay? So cool, we have a one-parameter family of deformations of your surface, so you can compute the derivative of the area. So this is now a function of one variable, of the variable t, and you can try to compute the derivative of this function. If you are a minimizer, this derivative is 0, of course. Okay, so that's the basic idea of variations in the calculus of variations. So now, there is a strict implication here. Area minimality implies first derivative 0. And then this is actually equivalent to h equals 0. So this is telling you something particularly strong. It's telling you that h equals 0, Newton's law, is actually part of being area minimizing surface, but is not necessarily equivalent to that. This is a super important point in the theory. Yeah? I cannot stress it enough. It comes up over and over again. So the derivative of the area, this is just a computation, linear algebra, changes of variables and stuff like that. And of course, I mean, I'm not going to explain the details here. You can find them in any book on these topics. Most of them, you will see the details. So the derivative of the area is going to be the integral over the surface of what is called the tangential divergence of the vector field you use to create this family of diffeomorphisms. So the tangential divergence, if you have never seen it, is the divergence, okay? You are just taking the derivatives. So divergence, you think about it in Rham as the I derivative of the I component. And now the point is that is the I derivative of the vector field scalar the direction of the component. That's how you should think about it. And then you just take an orthonormal basis of the tangent space at your surface, tau kappa, and then using tau k, you have tau k scalar the tangential derivative of x along tau k, you add up over the two directions, and you get this tangential divergence. And this is what it is. You cannot choose it, okay? I could have called it any other name. I've called it tangential divergence because it looks like a divergence computed in the tangent plane of the surface, okay? That's the choice of the name. But that's what it is. That's what you compute. You call it whatever you want. You get that quantity, okay? Integrated along the surface. Now, the reason why it's really a good idea to call it the tangential divergence is because you have a tangential divergence theorem, which is exactly as the divergence theorem plus the fact that you are on a surface. So how does this look like? The tangential divergence theorem is the integral of the divergence of a surface is the integral over the boundary of the surface of the vector field scalar the conormal. And this would be the theorem in Rn. The integral of the divergence in the domain is the integral along the boundary of the vector field scalar the outer unit normal. However, you are on a surface, and the tangential divergence theorem sees that, and that's where this mean curvature vector comes up again, okay? So it comes up, the mean curvature vector comes up in the previous, you remember in the previous derivation of Newton's law, I told you that the integral along the boundary of the conormal is equal to the integral of this mean curvature vector. And this is exactly another way of stating this formula, okay? Modulos, signs, or whatever. So there's probably a minus somewhere. Or depends on how you define things, I guess. So now remember that the vector fields we're working, they don't move the boundary of S. So this term is not going to be here, the term with along the boundary. So all you know if the derivative is 0, if the derivative of the area is 0, is that this first term in the tangential divergence theorem is equal to 0 for every vector field, which is 0 at the boundary. So only one option, H is equal to 0. That's an if and only if, okay, at every point on the surface. Okay. So this is how you derive the H equals 0 from area minimality. Questions so far? Does it all make sense? Okay. But actually, of course, I mean, right? I mean, why just being happy with that? Area minimality implies two things, at least. Implies a lot of condition in principle, but at least two things. And the other thing is the second derivative at time t equals 0 will be non-negative, right? I mean, why are we not even mentioning that, right? I mean, so it's clearly there is already something more, right? And what is the form of this second condition? First of all, it's an inequality. It's not going to be an identity. And now you may wonder, okay, what is this inequality? How do I reflect my vector field x, the fact that it holds for every vector field? What does it imply? So it implies this condition here, this integral inequality. So all that matters here is you don't see x anymore. What you see is a mysterious function phi. You can think of phi just as the normal component of x with respect to the surface. So essentially what I'm saying is that on a minimal surface, when you compute the second derivative, all you care about is the normal component of your vector field along the surface. And that's a scalar function, phi. So this will be a function phi from the surface with real values that is 0 at the boundary of the surface. And it satisfies a sort of weighted Poincaré inequality on the surface, right? So the tangential gradient of this function squared is going to be larger than the L2 norm of the function weighted by k1 squared plus k2 squared, which is the square norm of the second fundamental form of the surface, if you want to call it like that. So it's an interesting condition because I cannot localize it. I mean, I cannot take the phi out of the thing. So I cannot just say, but for every phi, this means that some quantity pointwise defined on the surface satisfy a certain inequality. I cannot do that, okay? But I have an inequality that must hold for every phi. Now, a super important fact, again, these are all classical, basic, central stuff. A cool thing about this problem is that when you have a surface S, okay, if you are a minimal surface S and you look at a piece of it, which is small enough so that it can be seen as a graph, okay, with respect to a plane. So imagine you have a complicated surface out there that does a lot of strange stuff, but then you go and look at it at a scale at which this surface is a graph. Then at the scale of graphicality, being h equals 0 is equivalent to be area minimizing with respect to perturbations in the cylinder of graphicality. It's the same thing. So this means in particular that this stability inequality, okay, if I look at it in a sense, in a cylinder of graphicality, with phis that are supported, so you need to follow here, I cannot really write it down too much formally because it becomes complicated. But it's trivial. So another thing that I know is that this inequality will be non-trivial only for functions phi that move my surface, okay, on a region where I don't have graphicality. At scales of graphicality, h equals 0 is all there is. But surfaces are surfaces. They can do a lot of things. They don't need to be global graphs. When they are not global graphs, h equals 0 is not the end of the story. Area minimality is stronger, and stability, so stable minimal surfaces h0 and the inequality are in between h equals 0 and area minimality. It's like an intermediate degree of information, okay? Good. Let's see. So let me explain why the stability condition is interesting. It's interpreted as a sort of way to tell apart observable minimal surface from non-observable minimal surfaces. That's the way to see that. And there is a theorem by Rick Schoen from 1983 where he uses the moving planes method, a classical PDE technique to prove symmetry of solutions to partial differential equations. And he proved that if you have a minimal surface in R3 whose boundary is given by two parallel circles centered on the same axis, then your surface has rotational symmetry. Therefore, h equals 0 become a nonlinear ordinary differential equation that you can integrate and you can find the solutions. And the solutions are that you're either a pair of disks, so your ODE is degenerate in this case because you don't really see anything, or when you can solve the ODE, you have two solutions. You have them only if the disks are close enough with respect to the respective ray. If they're far enough, you don't see them. You don't have these two solutions. But if they're not too far away, you have exactly two solutions that define what is known as the catenoid. You have seen the catenoid in pictures. It's easy, okay? Even if you do the experiment yourself at home, it's very easy to observe a catenoid. However, claim, it's very easy to observe the stable catenoid, the fat one. When you have the fat one, you also have the skinny one. The skinny one, you never see it. So there is a super cool experiment you can do, and people have done it and took pictures of it. So you start with two very close parallel circles of wireframe, and you generate a minimal surface. Then if you don't get what you want, you puncture it, and then you get a fat catenoid. The fat catenoid is absolutely area minimizing because it's like this tiny thing connecting the two circles, right? And then you start moving them apart, and the catenoid, as you move them apart, it becomes more and more bent inside, okay? And then there is, so if this, say that the circles have radius 1, when the distance is about 1.33 units of measures, the thing pops up and you see two disks. And then what they do, what they've done in this experiment, they've taken pictures as you move the two things, right? And as you move the two things, you can plot against the pictures the equation of the stable catenoid and of the unstable catenoid. And they become more and more indistinguishable. So in a sense, the unstable catenoid is what you is like, indeed, when the system becomes unstable and you transition from the catenoid to the two disks, okay, the two things are somehow the same. It's like the unstable catenoid and the stable, they're really close to be the same thing. You still observe the stable catenoid, okay? So what is this stability instability thing? Is, okay, what is a point where the model breaks down. Surfaces don't exist, okay? So you have a soap film, which is an object with physical dimensions, with all sorts of physical properties. You are kind of making an abstraction of it. But the model that you have created, you see, there are very high on uniqueness. Even for a simple boundary data, you have three solutions, okay? The first two are observable, very easy to observe in reality. The third one cannot be observed in reality. And one way of expressing that in the model is that it's unstable. So what does it mean unstable? It means that there are phi, fluctuations phi, right, that make the energy decrease. So, and a way physicists explain this is that you will never observe that because there is a normal deformation phi, which is something that is going to happen around the neck, right? Because around the neck you lose graphicality, right? And so that's where you want to put your phi, otherwise you're always in stability. So it's where you lose graphicality that you can do some action, right? So around the neck, you are going to do a perturbation of these things. Is going to decrease stability. So why is this related to reality? Remember that there is the bombardment of the air pressure, right? So it's like at each moment, the system is perturbed away from equilibrium because it's actually a dynamical system. And then the idea is that if there is a direction in the abstract space of variations that allows to decrease energy, eventually some of this molecular bombardment will have a positive projection in that direction, and the soft film will decrease its energy by following that direction. And then when it starts following that direction, it's a sort of catastrophe, and then you go away from the geometry you had and you transition to something else. But of course, again, so it's an abstraction, right? I mean, I'm deducing from an inequality something like a dynamical process that happens at a very short time scale, and so on and so forth. So unstable catenoids are not observed. So you see, Gauss computation, I presented this as deriving H equals 0 from energy minimization. In doing that, you actually learn something about the physics of these objects. So it's like why it's useful to work on these things. So,
sorry.
Yes.
There is no configuration in which the catenoid is stable, but it is not minimal.
So it's so no, there are. So there is a region of so is from remember I told you the parameter is if the radii of the circle are both 1 and the height, let's call it h. So for h smaller than 1, let's say, the catenoid is better than the disk. And then there is a value where the catenoid and the disks have the same total area, which is before the instability appears, okay? So, and there you have a bifurcation. And then you can still move a bit, then the catenoid still is stable, and it's just a local minimizer. The global minimizers become the pair of disks, okay? Yeah.
Okay, thanks.
And of course, I mean, this is plenty of examples like that, where you have local minimizers that are global minimizers under some conditions, but they stop being, and you have these transitions and so on and so forth. Yeah. Okay. So, what's next? Gauss, okay, derivation of the Young Laplace or minimal surfaces equation from area minimization. You do the calculus of variations, geometric calculus of variations, and you discover stability. And then there is 1873. Yes. Yeah.
In the moment when it pops,
Mm-hmm.
right, and you switch from the catenoid
Yeah.
to this, that's in that moment, catenoid is degenerate. I mean, or it really happens that
So
the neck of the catenoid is reduced to 0.
yeah, there is, I mean, the picture as I remember it, I've seen this paper a few years ago, but the picture as I remember it, you see something like an abrupt transition. So there are probably, I don't know the time scales, okay, but there is a time scale where what you observe is a minimal surface with a singularity and...
Is singular or before? So the catenoid, just before it splits,
Mm-hmm.
is it still a regular?
Yeah, it's a catenoid.
It's
Yeah.
not degenerate. It's not touching.
No, I don't think so. I don't think, but again, I don't even know how to answer this question because, you know, my understanding is that they're putting some high precision camera that they bought with a research grant in front of this thing, and it's taking pictures at an absurd frame rate. But then, even if you don't see it, it doesn't mean it's not happening what you are describing, because there are gaps.
Things
So
becomes really fast.
yes.
At that moment, the catenoid is still not degenerate.
I don't think how you see it from experiments. So I think you would need probably a theory, and I don't know. I mean, it seems to me a delicate, a very interesting question. But again, what drives? So because here you have this strange dynamical process where you're really seeing something because you're changing the boundary conditions continuously in time. I guess you have to do that very slowly because so I really don't know what is the physics of that. Like, how would you try to model that? This I don't know. Yeah.
Tell me if I understood correctly.
Mm-hmm.
There is a positive time
Mm-hmm.
in which the catenoid is only a local minimizer.
Yes. And you
then
keep observing it because
and
just
you keep
the
observing the catenoid because you're coming from a catenoid.
Yeah. It doesn't. It's not that the minimal surface knows that somewhere else there is a way of minimizing
Exactly.
energy and jumps there. Okay.
And then there is a positive time,
Yeah.
and then there is the pop.
Yeah. Then there is a time in this experiment or a distance between the two disks where being a catenoid becomes unsufferable. Okay. Yeah. And the probability, I think it's more probabilistic. It's like once you are the neck is thin enough, the probability of this thing
becomes higher and higher.
and it does. It has a thickness too. Huh? So again, the physics literature is a gold mine of stuff like that. Okay, you just open it and there is people taking pictures of all sorts of things today. I mean, not only on Instagram, also in the labs. Okay, people do that. So do all sorts of things. It's very interesting for me. So Plateau, actually, we have this beautiful picture. Actually, did the obvious thing. I mean, you do soap films and you see singularities. It's not just h equals 0. That's evident to anyone that has never done soap films. It's not just h equals 0. Okay, it's actually very easy. If you think about it, it's so easy that I did it in my kitchen. So you see, this is not h equals 0. So here you can see there is an angle. Okay, and this is not a fancy experiment. This is really with soap and water and wireframe. Okay, so here there is something. Here there is an angle. Here there is a line of points that is maybe barely visible. Here there is a line of midpoints where something else happens. So it's not true that H is equal to 0 and that's it. Because it's not true that you are a surface. Okay. So, and here there is a better, much fancier picture. So you see, if I do a skeleton cube of wire frame and I dip it in soap, this is what I see. And along these lines, you see where this kind of surfaces with H equals 0, we guess, meet, you are not a surface. So H equals 0 what, right? So the idea, Plateau described what's going on here in a very simple terms. He said, okay, all that you are observing with soap films is, yes, H equals 0, but these smooth surfaces with H equals 0 can meet in 3 along lines of points that don't need to be straight lines, really can be curved lines. But if you blow up at one of these points along a curve, what you see is a line, the blow up of the curve, and then you have 3 surfaces, 3 half planes meeting at 120 degrees. And now, once you start having a line of y points, this line can be closed. You can have a circle of y points, say, or something like that, but a closed curve. Or this line may have endpoints. And if you have endpoints, at an endpoint, you see 4 of these lines that blow up a tetrahedral, what is called a tetrahedral singularity. Is what you observe is the cone of a regular tetrahedron, that here is dashed, over the center of a regular tetrahedron. Okay? So that's his prediction. That's all you see. You can't see anything else. And in this picture, we see it very well, right? So there is a ton of lines of y points, and then here you see the corners of these sort of, there is, down in the middle of the picture, you can see something like a quadrilateral of soap that is kind of, the picture is taken so that you almost don't see it, it's almost transversal to it, but there is going to be a sort of quadrilateral of soap in the center of this picture, okay? And the corners of it are T-points. So this is a minimal surface with 40 points. And now, of course, I mean, the question arises, I mean, how is this even, so what happened to Newton's law, you know? I mean, what is the balance of forces for this system, right? And so on and so forth. So, and actually, the question, understanding Plateau laws, in which sense y points and t points obey the Newton law at equilibrium, balance of forces, okay? If you want, this is the starting point from a very GMT viewpoint. I mean, this is a school in geometric measure theory and application. From a GMT viewpoint, this is the starting point for the theory of varifolds. So this is the point where you see the distributional formulation of H equals 0. So let me explain how this works. So for example, let us consider a surface that consists of 3 half disks meeting along a segment of y points. Okay? So in this case, the wire frame is 3 half disks of wire frame, and I put them exactly at 120 degrees because I want to observe the y cone, just a section of it with a boundary datum. Okay? And if you do it, that's what you observe. That's super easy again to do also at home. So clearly, what I observe is not a surface because of this line of points L. This is not part of the wire frame. L is really points where the soap surfaces meet and do something different. Okay, but now what I can observe is that H is equal to 0 on each of the 3 things because they're going just to be pieces of plane. Again, this is also observable easy. But so the question is not why forces are balanced over S1, over S2, or over S3. Is why there is a balance of force along Y. Where do I see that? Okay? So, so let's call S the union of these 3 half disks. So we're going to take from Gauss, remember that Gauss told us that H equal to 0 is the same as saying first derivative along any variation equal to 0. It's the same thing. So we are going to take that as our definition of, as our balance of forces equation. Because we know that in the only other case we know, the smooth case, we know that that's equivalent to H equals 0, which was a legitimate balance of forces, right? So let's take that as our balance of forces. And now you see, you may object, okay, you're taking a vector field S, defined on S with values in R3 that is 0 at these boundary circles. you integrate the tangential divergence, but how do you even compute the tangential divergence of the vector field x along S at points on L, right? Because on L, there is no unique tangent plane. So how do I compute the tangential divergence, right? Integration over L, the tangential divergence, I need an orthonormal basis tau 1, tau 2 of S, and I don't have it there because I don't have one tangent plane. The answer is I don't care, because L is a line and the area of a line is 0, and I'm taking an integral, so who cares? Okay? It's an integral condition, okay? And the integral is taken over a two-dimensional domain. So what happens on a line is immaterial, which is effectively like telling you that this integral of the divergence you are just taking separately on the smooth minimal surfaces, right? And then the only difference is that now I have 3 integral of divergences on different surfaces. And now on each of them, I apply my tangential divergence theorem. What else can you do? So when you do that, since these are minimal surfaces, right, you don't see the term with the H term. You just see the conormal term, right? Because this would be the tangential divergence theorem, but the H is 0. So actually, you see, here is not even important that S1, S2, and S3 are pieces of planes, okay? It's just 3 minimal surfaces meeting along a line. You get the same computation, okay? And then the other interesting thing is that now, what is the boundary of Sk? Well, the boundary of Sk, each one is a common part of the boundary, that is the line L, and then there is the boundary you have up there, right? But now, on the boundary up there, what I call the boundary up there, x is equal to 0, because I'm not moving the boundary of the wireframe. But x is moving L in principle. So I'm considering the formations that, oops, I'm falling down. So I'm considering the formations that are moving the line L, right? So this integral is actually the integral over L, and then when I realize that the only part of this boundary that matters is L, I can just bring the sum inside, because it's the same domain of integration with different integrants. So equilibrium will mean that this sum of the conormals, so you see along the line L, I have 3 conormal vectors, 1 for each of the 3 surfaces that is coming in, okay? And what I am discovering is that this tangential divergence is the integral over the line of x scalar, the sum of the 3 conormals. But now remember, Plateau law is that the conormals, right, meet at 120 degrees. So if you have 3 unit vectors meeting at 120 degrees, you can do the computation, the sum of the 3 vectors is 0. If you have 3 unit vectors, okay, and their total sum is, it's an if and only if. If you have 3 unit vectors and you add them up, the sum is 0 if and only if they have the 120 degrees condition. Otherwise, there is a mismatch and you see something. Which means otherwise, so if I imagine to move my boundary datum a bit continuously, only on 2 circles, so I'm kind of forcing a change of the angle, right? It's like I am unbalancing the object, and then one of the 3 half circles along the boundary line is pulling the rest with surface tension. And then the thing changes. You can understand it like that. But at equilibrium, so you see why Plateau law. Plateau law is because if they meet in 3 and they are at equilibrium, what does it mean at equilibrium? It means this integral formulation of the Newton's law, then there is only one possibility for these 3 normals. Okay? Once you've understood y points from the point of view of Newton's law, you don't need to understand t points, okay? Because you can't. I mean, you don't really see t points from this computation, okay? So this is really a computation just good for the y points. It doesn't really explain the t points, unfortunately. Actually, what is even more disturbing is the next slide. This computation is fine for y points, but is fine for a ton of other things. So, for example, my super cool computation, imagine that your surface is obtained by 2 planes, just intersecting at any angle. Then I do my little computation, right? I do S1, S2, S3, S4, and then the sum of the conormals is going always to be 0. So that's really kind of a bummer, right? Because it tells you that, okay, yeah, you were able for 1 second to say, Plateau law is just Newton's law, but it's clearly much more. Because Plateau law is something that is telling you you cannot have 7 minimal surfaces meeting along a line, and then when you add up the 7 vectors, the angles are 0. It's not telling you that. It's telling you it's just 3. Okay? It's telling even more, that these lines of y points, when they end up at an end point, you see exactly a regular tetrahedron. But this is not Newton's law. So I think this is super cool, because it's really telling you that it's not just the balances of. We have already seen it with the stability, right? Even the stability, the unstable catenoid, you don't see it, and but it satisfies H equals 0. Theoretically speaking, it's an equilibrium configuration, but it's just not observed. So here again, there is something like that. It's like the same unstable catenoid effect. So for example, a singularity like any number of planes meeting along a line would be, in a sense, absolutely fine for H equals 0 in this distributional form, but is clearly not okay for reality. So there is something more going on. Okay? So, so if the Plateau law is more than Newton's law, then what is it? That's the question. And let me give you straight an answer, which I don't think is necessarily a physical answer, okay? But it's at least a mathematical answer. So, and it's this definition by Almgren. So it's a bit like Gauss, okay? Gauss tells you that H equals 0 is related to area minimization. It's implied by area minimization, okay? And now we are saying that H equals 0 is more than Plateau law. It's more general. So, and now Almgren say, okay, you can relate Plateau law to area minimality. So let me give you the real definition. So I'm not going to write area, kind of formal definition here. So let's say that we have the n-dimensional Hausdorff measure in Rn+1. We only care about n equal 2, essentially. But let's say you can formulate this in full generality. So you have a closed set in Rn+1. You say that it's Almgren minimal. Of course, Almgren wasn't calling them Almgren minimal. Okay, we call them Almgren minimal. I mean, the guy was his own piece of work, but he didn't call the sets after himself immediately. So Almgren minimal in an open set omega, if Hn of s is less than Hn of f of s, for every map, Lipschitz map from your open set into itself, which is different from the identity only in a compactly contained subset. Okay? So this is area minimality, right? I mean, it's if S is just a nice surface, okay. So what's even the difference with my definition with Gauss and the diffeomorphisms, right? So this is a strange definition, because the thing that matters is the one that is not written explicitly on the definition. That's typically of Almgren, right? So it's like the point is definitely not on the page. You can be sure. So, and the point, of course, is not that the map is Lipschitz, which is a technical thing. It's important, but it's not really technically important, but not the point. The point is F is not asked to be injective. That's the key point. Okay? Because you see, if you have two lines, that is the kind of singularity that is incompatible with Plateau laws, but is not incompatible with H equals 0 in distributional sense. If you have two lines, and you start doing diffeomorphisms of them, and you compute the area of what you're doing, but the area doesn't care about the fact that the two lines overlap, right? If it's a diffeomorphism, it's like you're doing separately on each of the two lines. So you will never see anything. I mean, it's just going to be fine. But the point is, how do you beat two lines in terms of area minimality? You beat two lines, for example, here two planes. I'm seeing them as two lines like a cross. And you see, I can beat them by doing a variation that, say, fixing these 4 points as my boundary datum, by creating two y points. And the two y points will have less length, and then less area if you start doing this in higher dimension, okay? But, and that's the point, how do I see this red object as the image of the blue object? There is a change in topology, right? Because before I had an object that I could disconnect in 4 components by taking 1 point, and now I have an object that doesn't have that property anymore. The worst I can do to it is taking 1 point and get 3 components. So there is something that doesn't add up, and indeed I have changed the topology by using a non-injective math. So it's important that these Fs are not homeomorphisms. Otherwise, there is no way of killing the configurations that Plateau didn't allow us to consider, okay? Okay, this is just, however, this is just an idea, okay? So what Almgren proved is what is technically called a partial regularity theorem. Essentially, Almgren proved that in any dimension, an object like that is going to be a minimal surface outside the set of area 0, okay? A closed set of area 0, which is, of course, a very poor information because we're very, very far away from Plateau laws. However, Jean Taylor in 1976, she proved a theorem that in this kind of line of work is the best theorem ever, okay? You can't beat Jean Taylor's theorem. I mean, it's the most beautiful result in this area of geometric measure theory, by far and forever. So what she proved is that in dimension 2, an Almgren minimal set in some open subset of R3 is a locally finite in omega union, so is a finite union of smooth minimal surfaces that are C1 alpha joined by lines of y points, and if the lines of y points have endpoints, those are T points, period. So Almgren minimality implies Plateau laws. Amen, that's it. You can discuss on the C1 alpha. Actually, you have analytic along the y points, and then at the T points, I don't think anyone has ever proved it. But I was talking with Nick Edelen while we were walking from this building to the Mensa, and we convinced ourselves there is a proof that it's really C1 alpha for the T points. So near the tip of the T point, there must be a critical alpha that it's kind of life is telling you that. Okay, you cannot really do it better. But again, this is all pointless. Okay, the point is that, and C1 alpha. So yeah, C1 alpha joined by lines of y points, and that's it. Yeah. So this is the theorem. Now, it's not that after Jean-Taylor theorem you have closed the shop here. Okay, so because the next question is, this is super dangerous. I'm going to die. So, or I'm going to follow Andre. So, Jean-Taylor's theorem, however, is not the end of the story. Okay? It's not necessarily the end of the story. I mean, there are so many ways it's not the end of the story. But one of them is how do you relate this notion of Almgren minimality with the Plateau problem itself? So I've never mentioned the Plateau problem so far, okay? But there is a Plateau problem out there, which is actually has nothing to do with Plateau. Okay. Okay, let me, before I tell you about the Plateau problem, that's a fun slide, okay? Just for, we have done all the work to arrive here. So I have a theorem with Jacob Bernstein, proved a few years ago. So we took Schoen's theorem, but rather than considering smooth minimal surfaces spanned by two disks, our surfaces are kind of semi-classical surfaces, like smooth surfaces plus y points and T points. So it's an intermediate class between being smooth and being a varifold, stationary varifold and stuff. So it's the, okay? In this class of surfaces, we have proved that if you start with two equal radii circles on the same, centered on the same axis, parallel, then there are only 5 possible Plateau surfaces that are the 3 that Rick Schoen found. Then there is two catenoids with a singularity, 2 singular catenoids, a fat one and a skinny one. Okay, so the fat one, super easy to observe. Actually, I challenge you, in your kitchen, try to do the experiment, okay? It's 9 times out of 10, you see the singular catenoid, then there is 1 out of 10, you see the 2 disks. If you really dip the thing, essentially the 2 things orthogonally, and you come up vertically, then they don't realize each other's existence, and you see 2 disks. But as soon as there is a bit of an angle, you're going to see the singular catenoid, actually, which has way more area than the catenoid, because there is also the floating disk. And then you can have fun and puncture with a pencil the middle disk of soap, and this thing is going to jump into the fat catenoid. Plop. Okay? So, configuration C, unstable. And this is classical. Okay, so I think that people doing the calculus of variations of the old times knew that the other catenoid is unstable, has been knowing that, I don't know, time immemorial, okay? Now, this other guy, I don't know. So what is wrong with the singular catenoid, the skinny singular catenoid? I am not exactly sure. I realized this while I was preparing the slides in my own time zone that at this point is undefined. For me, it's like 3 a.m. Right now. So I really don't know, because you see, here the catenoids are attaching at 120 degrees, right? So it's way before the catenoidal neck realizes it's not a graph, stop being a graph. So what I'm saying is that the top part of the catenoidal neck is globally a graph over an annulus. So I maybe be missing something because it's 3 a.m. for me, but it could be that there is something I don't see. But I don't see it unstable in itself. I don't see that the top neck being unstable, clearly the bottom neck being unstable, clearly the disc being unstable separately. However, I don't think we are going to observe this guy ever, right? Because why would it want, once the system is in this topology, why on earth would it prefer the one with more area? I mean, it's, right? It's, so my question is, physically, why we are never going to see E, right? And I have run out of conditions here, okay? Because this guy, I think it's an Algren minimizer, at least locally, okay? Maybe yeah, there is a map F taking this into that, and so it's not globally an Algren minimizer, but locally it is. So, I mean, how do we kill E? Okay, maybe this is a stupid question. Maybe it's super, I don't know. But for me, it's a question at this moment of my life. It's a question. Then I don't know. It's maybe.
You asked if it's stable.
Yeah, what's wrong with it? So why don't we observe it physically? I don't think you observe it physically. I don't believe it. What?
Are there other critical points with the same topology?
No, these are all, so that's my theorem with Jacob. I mean, there are 5 critical points.
So this means that you can go from the
Skinny singular to the
other one,
yeah.
increasing the energy, because otherwise there would be a mountain pass somehow.
Oh, right.
If they're both stable, there would be something else.
Yes. Yeah.
And you tell us that there is.
But that's what I don't see, because stability is these inequalities, right? And now, they don't seem to violate the inequalities. So. Yeah, no, I think you're right. I think you're right. But it's somehow not. What I'm saying is that the physical reason why, yeah, it's that one, but I don't see in what I've said so far. So what I've said so far is good to kill the number C, but not to kill exhibit E. So I don't know.
And maybe the mountain pass would be unstable regular catenoid.
Huh? The regular one,
Yeah.
but that changes the topology, right? Because you have the.
But can you keep the topology doing min-max?
I don't know. Well, definitely, yeah, the physical system would do that, right? I don't know, because. So I don't know if it's even a well-posed question. So let me move on, because I don't know what I'm asking, okay? But somehow there is a very intuitive point of view on all these things that is the one that I've adopted so far, where I don't see exactly how I get rid of that, okay? But I don't know. I mean, we have so many more things to talk about in the 90 minutes we have. So how much time do we have?
It's 7 past 10.
20 minutes, something like that. 50. Okay. Okay, so let's talk about the Plateau problem, which is really the Plateau problem because Plateau never cared about mathematics. I think it's experimental physicist. I have opened his famous work. There is not the faintest trace of a PDE anywhere, so, or infimum of this or that. Okay, so I think he genuinely wasn't necessarily thinking about that. But anyway, so the Plateau problem, definitely Lagrange was considering it 200 years before Plateau. It's giving a wire frame, a curve W in R3, find an area minimizing surface, or more than one if there is more than one, which have W as their boundary. And there are several solutions. So essentially finding solutions to this problem, showing that this problem is solvable on certain classes of curves W, okay, has been one of the driving, motivating problems of geometric measure theory. So a ton of techniques and questions have been developed trying to answer this question. So Douglas and Radau in the 1930s, and now this is start becoming ambiguous because we're almost there with the 2030s, right? So in the 1930s, Douglas and Radau, they solved this problem in a class of surfaces that are images of a disk. So you have a disk B2 in R2, and you do a map from the disk in R3, and then the area of your surface is going to be the integral over B2 of the Jacobian of this map that here I have written with like the wedge product of the two derivatives, absolute value. And then there is the super cool trick that since you are in dimension 2, okay, if you take the same boundary data, but you do this with conformal coordinates, so you change u, the u that is here is not the u that is there. So it's just same boundary datum. But there is another u with the same area, and you can write the energy as the Dirichlet energy. So that's amazingly lucky trick. And you're not done, because of course if you want to do the compactness for a sequence, minimizing sequence, right, you have the problem that the compactness, you know, there is the diffeomorphisms of the domain itself that enters in. So it's a delicate problem, but they evidently in the 30s, Douglas I think won a Fields Medal on that. So they proved the existence of solutions for this problem. Then there is the approach with sets of finite perimeter that De Giorgi completed by the end of the 50s. By the end of the 50s, he had the regularity theorem, the existence in the regularity theory, and the approach with currents. So sets of finite perimeter kind of solve the problem for general N. The approach with currents solve it not only for a general N, also for higher codimension, and with way more flexibility in prescribing the boundary datum. But from the point of view of Plateau laws, the big limitation is that all these approaches in dimension 2, the solutions are smooth. So you minimize area and you get something smooth, which is actually the reason why they are useful in other contexts. Okay, so the theory of one of the uses of the theory of currents, okay, is you are in some manifold and you look at some homology class for surfaces in the manifold, and then you want to show, and then you have topological surfaces that are representatives of this class if the class is non-empty. But how do you construct a smooth surface with that topology and blah, blah, blah question? By doing area minimization in that homology class. So by minimizing the class of currents, you will preserve the homological constraint and you will find a minimizer. If the dimension is small enough, the minimizer is going to be smooth, and the differential geometry is happy because it can integrate its differential forms on it. So it's success. You want to do min-max methods that were mentioned by Andrea one moment ago. Again, having, generally speaking, smoothness waiting for you out there is a plus, it's not a minus. Absolutely. So, in a sense, the fact that these distributional approaches to the Plateau problem produce smooth area minimizing objects in dimension up to whatever it is, Simon's cone is the first problem that it's unavoidable, it's a plus of the theory. It's a good thing. But if you were trying to understand actual subfields, it's bad, because you do all the area minimization, you will never see Plateau laws. There are ways around that. Currents modulo 3 are compatible with Y points, but then again, it's a different story, because you cannot see the T points, and then I won't even enter into that. My shortcut here is pointing you to a paper by Guy David, 2001, that is called "Should We Solve the Plateau Problem Again?" So this was published in the Princeton series of whatever, okay? So it's not that, this is not fringe literature, it's not a Facebook post. This is a very serious work, okay? And it's called like that, okay? And definitely Guy David knows about currents modulo P, okay? So, and he's asking the question in the title. And of course, it's a rhetorical question. The answer is yes. Because the area minimizing schemes that we have don't get to see the Plateau laws as we would like them to do. So, a solution, and And Almgren has worked on this question for a long while. If you go and see the literature on what is called size minimization, you will have a taste of attempts more or less successful in that direction. I think the first clean, satisfactory solution to this question has been provided by Ginny Harrison and Harrison Pugh in 2013 by the introduction of what is called the homotopic spending condition. And this is where I started being interested in these things. When I saw their paper, and then I was visiting Camillo, and I told him about the paper, and we got excited, and we wanted to understand it. And so we found an alternative, not really an alternative proof, somehow bit conceptually different proof of the result, and then we started working on these things. Okay, so what is the Harrison and Pugh approach? So you start with a closed set. This will be the wireframe. Notice that it's just a closed set. I'm not telling you it's a curve, okay? It could be the skeleton of a cube, like in the fancy example of before. It could be something three-dimensional, which is actually a super cool option, if you think about it, because wireframes are solid physical objects, and the length scale that they have, right, that their thickness is they're much thicker than the soap film. So it's physically more accurate to think about the wireframe as a solid object, okay, rather than a curve. So closed set. Then you call omega the complement of this open set. This is the region that is accessible to the soap film. Your soap film will be somewhere, but not inside the wireframe. That's all I'm saying. And then what is the soap film is a closed set. Oh, there is no soap film. So, okay. The soap film will be a closed set S contained in the complement of the wireframe omega. Okay? Now, how do we say that this closed set is spanning the wireframe? We introduce, and this is the homotopic spanning condition. We consider embeddings gamma of S1 into omega. So these are, you can imagine them at little curves, embeddings of S1, but in omega. So they don't cross W. So if W is a sort of solid torus, as in this picture, gamma could be one of these curved link to the torus. And then the family C that we consider families that are closed by homotopies in omega. So it means that if I put a curve gamma in my class, you see gamma 1 and gamma 2 are homotopic to gamma inside omega. So I can deform gamma into gamma 1 continuously without ever crossing W. They are homotopic. Therefore, if gamma is in C, gamma 1 is in C. Now, in this case, there is nothing else. It's just gamma and all its friends. Okay, but you see, the gammas that I have here, right, they could be super close to the wireframe. I could do one that kind of explores with the region in between. So they're really spanning the gammas, okay? The area around the wireframe. So, and then we say that a set, closed set, is C-spanning, so it's spanning the wireframe with respect to the class C, which may be confusing because now you can say, but there is only one class C. What's the problem? You will see in a second. There can be wires for which you have multiple choices of this class C. Okay? So S is C-spanning W if it intersects all the gammas in the class. So you see, a set S to fill the hole, what does it mean that it spires W? It fills the hole. If my set is like a disk, but then it misses one point, then I can make gamma cross through that point. One gamma that is in the, and will not intersect, and then I don't have the spanning. So if there is a hole, even if I just miss one point, this thing will detect it. Okay. So, and the Harrison-Pugh problem is down here. We minimize the Hausdorff measure of sets S that are closed and are C-spanning W. Okay. This is fantastic. You don't need distributions. You don't need, I don't know, you don't need to take a derivative, right? You don't need to find, it's Hausdorff dimension, closed set, embeddings of S1. There is nothing on the blackboard, okay? So it's like the simplest possible formulation of the Plateau problem you can dream of in terms of technology needed to formulate it. And it's satisfactory because this idea of homotopic spanning is cool. So these are a few examples. So let's play with W's that are given by a bunch of disks in the plane. So in the plane, two disks, gamma just wraps around one of the two disks. And what is the solution S? It's going to be a line. A segment joining my two disks with 90 degrees is going to be area minima. But already you see, if you have 3 disks and you have gamma 1, gamma 2, and gamma 3, you need all 3 of them. If I miss one, of course, I just do a segment, joining the two. So if I don't put, say, gamma 1, the solution will just be a segment going there. But if I put all 3 of them, my surfaces S, they will need to join, okay? And then this is going to be the minimizer, a triple point. And now you see 4 disks, you see what I was saying. There is not only one choice of C. If I have 4 disks and I use gamma 1 and gamma 2 like this, I'm just going to do that. But if I also add as a generator this gamma 3, that kind of wraps around 2 of them, you see gamma 3 now can explore the whole region in between, and these 2 segments will not intersect some of the cars in the gamma 3 class. So this, even if this has much less length or area, okay, if you imagine it in higher dimension, the gamma 3 will force something like a singular catenoid. So you see, so there are multiple choices of C, and depending on what you choose, you may see 2 disks or the singular catenoid. That's the philosophy. This is super nice. I think it's very, very nice. Because it's like the choice of C, you can think about it as how am I taking the wireframe out of the SOAP solution is how I choose C, okay? That's my intuition of it. So, and the theorem of Harrison and Pugh, and then Camillo De Lellis, Francesco Giraldini, and myself kind of work more on these and contributed to ways of extending these higher dimensions, higher codimension, more general energies, and so on. And then so it's kind of a literature. It's like 7 or 8 papers where you do all the possible cases, okay? But the first paper we did was reproving the Harrison-Pugh theorem and actually proving the same existence theorem for Guy David's favorite formulation. It's called slide minimizers. We partially solved this problem. So it's a very complex topic, okay? So I don't want to oversimplify. I'm kind of oversimplifying today a lot. A lot of things have been brutally simplified in my presentation. But so let me not exaggerate. But I just want to point you to this paper with Camillo and Francesco. So the theorem is there exist minimizers for the Harrison-Pugh. As soon as the infimum is finite, I haven't put the assumption, but as soon as the infimum is finite, you have minimizers. And these minimizers are under minimal sets. Okay, so in dimension 2 and 1, they satisfy the Plateau laws. And you can have fun and prove that they look exactly like this. Okay, so that's the. So.
And you put this in any dimension of a dimension of a very general result?
Okay, in the paper that I work on, we did this in codimension 1. Then there is papers by, and then I've lost track. So there is De Rosa, De Filippis, Giraldin. They did this in higher codimension. Then there is another combination of people that did that for anisotropic integrants in codimension 1. And then there is another paper that is anisotropic integrants in generic codimension. And each time there is something in our proof that breaks down, and you need to find an alternative route. Okay. So, yeah.
Do you still use S1 in higher dimension? Like
No, they become spheres. It's in higher codimension. It's not circles. It's spheres. It's of course. So it's a whole thing. Okay. Here I kind of I'm keeping it on the Plateau laws essentially. So let me show. I probably have 5 minutes. Let me give you an idea of the proof. Because you cannot cheat. I mean, it's not that you have done sets of finite perimeter currents because, you have done them for a reason, because you want compactness. And you want compactness in a class where your limit is still a surface. Here, what do you have? You have nothing. You have closed sets of which you compute the Hausdorff measure. Who is going to give you compactness? And why does the limit of a minimizing sequence going to be remotely an object like the one you started minimizing from? So I think that's a super important point, because otherwise it seems that I'm selling you this magic thing with the little cars and it all works. So the point is that there is like 50 years of geometric measure theory and all the possible tricks of the trade, and then you can avoid, doing these other things, okay? Why you can avoid them? Because you recycle all the competitors and smart geometric ideas in this setting. And you discover you didn't need a lot of fancy stuff. Okay, so the first proof that the way it's presented in my paper with Camillo and Francesco. So step one, you consider minimizing sequence. So these are just closed sets that are C-spanning. So their Hausdorff measures converge to the infimum. So which means essentially that you have a sort of perturbed minimality property. So the area of each of these Sj is going to be less than the area of any competitor plus an error, a small number. So it's a sort of minimality inequality with an error. So it's useless unless you pass it to the limit. Then it tells you something. That's the whole idea. So, and this is very typical. So when you try to do existence, and this is, I mean, I'm stressing this for the students. There is plenty of situations out there. Manford-Shah problem is one of them, where you don't necessarily have immediately available a distributional theory that clearly works for you. So in these situations, the do-it-yourself approach, where you don't have a fancy compactness theorem, okay, to work with, but you just improvise. How? You use the fact that the minimizing sequence has a almost minimality inequality, and then you do the regularity theory, so the competitors that you would use to prove the regularity of the minimizer, you use those competitors on the minimizing sequence, plus the error, and then you send everything to the limit. And so somehow you are building, using the regularity theory, you do the existence, and then the regularity too. So it's like, so the direct method is this fancy conceptual thing. We start with the minimization class. We relax in some distributional class. In the distributional class, we have the big general compactness theorem. And then we do the regularity and we show if we are back in the smooth class. Here it's like we do everything at the same time. You do the regularity to prove the existence. It's all together. We didn't invent that. Huh? I don't know where it comes from, but definitely we didn't invent it. So,
it's clear that you know the fact that you are in dimension 1, you use the regularity result in dimension 1.
No. This all can be done in any codimension for integrands where you don't have, but because you just use the simplest, more robust elements of regularity theory. Let me show you. So the compactness that we have is just, we consider the radon measures that are the restriction of Hausdorff measure to Sj. There is a J missing here, of course. So this is Hn restricted to Sj. And now, okay, these as radon measures, they're just the integration over Sj. Here there is again a J missing of continuous function. But they have bounded energies, right? Mj of omega is finite, is bounded in J, because the limit converges. So there is a weak star limit, mu, which is just a radon measure. So who tells you that if you have a sequence of surfaces, you look at them as radon measures, you take the weak star limit because they have bounded areas, who tells you that the limit is still a surface? The answer is no one. And it's generally horribly false. Okay? So it's not that you can, it's not that, there is nothing magic here, okay? It's all the rules of physics still apply. You can do this. Is leading you nowhere, okay? So, trivially, the Harrison Pugh is the limit of the energies. These are the mu j's of the omega for this sequence of radon measures. This is good, omega is open, is going to be more than. So the lower semi-continuity is still there. The question, non-trivial goal, is showing that this measure mu is larger than Hn restricted to a set S, which is closed and C-spanning. Then I'm done, yes. How do I prove that? That's the difficulty. And that's where we're going to use this perturbed minimality inequality. Okay? So the goal now is learning stuff about this measure mu, that showing that it's not really arbitrary. It has a lot of properties because it comes as a limit of a minimizing sequence. So, and the first thing is like, okay, take a ball. Any ball disjoint from the wireframe. The minimizing sequence property tells you that if you start from Sj and you construct sets Sj tilde that are C-spanning and agree with Sj outside of the closed ball, then I can eliminate the area outside of the ball, I can cancel it, and I have this minimality inequality, right? So for each Sj, I fix a ball, and for each Sj, I do something inside the ball, closed ball, and I keep that, and I get this minimality inequality. So choice number one, it's what are called the cup competitors. So imagine that Sj is this kind of thing here, and this is my ball. So what I do, I look at the connected components on the sphere, on the boundary of the ball, that Sj is cutting. So Sj is a closed set, so there is going to be a bunch of open sets. For almost every radius is going to be countably many open sets. So there are a ton of almost everywhere here, okay, but who cares? So, and then essentially I just take all of them. So outside of the ball, Sj tilde will be exactly Sj, and then inside the closed ball, I take all the connected components, but the one of largest area. That one I throw away. Okay? This is the cup competitor for Sj. And now I know if I can prove that this Sj tilde is still C-spanning, then I have a minimality inequality that's written here. Okay? So cup competitors. So we clean up, okay, everything that is inside Sj's goes away. We throw it away. And we just look at 1, 2, 3, 4, 5 connected components. We take the 4 that are not the largest area. One is the largest area. That one, we keep it away, and we save. Of course, if I could say, OK, let me just put the whole sphere, but let me try to save a bit. At least the largest component, I throw it away. To save a bit of area. I want a competitor that is not entirely stupid. OK, that's the idea. So I'm trying to get some information. So now, is this thing C-spanning? Is Sj tilde C-spanning? Take a gamma in the class. If gamma was intersecting Sj outside of the ball, then it's fine. It still intersects Sj tilde, because outside of the ball, I haven't changed anything, right? So the problem is if I have a gamma that was not intersecting Sj outside of the ball, but somehow only inside of the ball. So what I'm saying is that the gamma to the left is fine. Outside of, so now I have a gamma that intersects Sj inside of the ball. Now my claim is that if gamma intersects Sj inside the closed ball, okay, then it must have the following topological property. It must be entering the ball from one of the connected components and exiting the ball from another connected component. And since I have taken just one of the connected components away, every curve gamma that intersects Sj inside must also intersect the cup competitor. But how do I prove that? If a curve gamma intersects inside the ball has this property of coming in and coming out from two different components. Well, the reason is that, okay, if it does that, it's fine. If it enters from this one and exits from that one, it's fine. So the problem is if I have something that enters from this one and then exits from the same connected component that I've taken away. But for that one, I am gold, right? Because if that's what you want to do, I can homotopically perturb you away from the ball without ever, right? Without ever touching the other components. I can just push it outside, and then I have a new curve gamma that is homotopic to the first one, so it's still in the class C, and doesn't intersect Sj anywhere, because it wasn't intersecting it outside. It was doing it inside, but I can push it out. Cup competitors are good. And it's all arguments like that. It's all topological stuff like that. Very elementary, but still you have to do it. Okay, now that we know that we have them, we look at what the inequality says. So the area of Sj tilde inside of the ball is actually the area of Sj tilde on the ball, on the sphere, right? Because inside the open ball, it does nothing. And now look at this thing. So what is the area of Sj tilde over the sphere is the area of all the connected components minus 1, the one with largest area. And now there is a little trick with the spherical isoperimetric inequality. So when you are on a sphere, you have an isoperimetric inequality. The volume of the set is going to be bounded by the perimeter of the set with the right powers. However, there are two sets, because now the sphere is compact, right? So for each set, there is the complement of it, right? So, and the isoperimetric inequality is always going to hold for one of the two choices. Which one? So here the fact that I took out the component with largest volume plays a role. allows me to apply the spherical isoperimetric inequality. And so the area of the cup competitor on the sphere is going to be bounded by the area of the boundary of the cup competitor, okay, inside the sphere to the right power. And now, you see, the boundary of the cup competitor is just these two purple points, is less than the trace of the original guy on the sphere, because I have closed a lot of gaps while I took the union of all the connected components. So the area of Sj inside the ball is less than the area of the trace of Sj on the sphere to the isoperimetric power. This is super cool. Plus the error, that I forget the epsilon j, plus the error. So this is completely useless if r is very small with respect to epsilon j. Completely useless, because it's kind of an information above a certain scale. But look at this with the epsilon j that I forgot to write. So give a name to the function on the left-hand side, fj of r, that's an increasing function. And this is less, the area on the sphere is less than the derivative in the radius of this function, computing the area inside of a ball. So as the area inside of the ball is computed, I have an estimate between how much area I have and how much this area is growing. It's a differential inequality with this power. So, do you know a function that does that? Is r to the n. R to the n, this becomes an inequality, okay? So the area is growing like r to the n. Now it's an inequality, from which side? And there is still the epsilon j. Okay, so you send j to infinity, and this is really basic stuff, Fatou and monotone functions, so basic measure theory. And you discover that f of r, the one for the mysterious measure, so this is mu of br now. We know nothing about it. There is no way of doing variations of any sort, okay? So mu of br still has the same differential inequality. And an increasing function with this differential inequality is growing from below, is bounded from below by a constant times r to the n. Now this is something. So because this measure mu is not just a random measure, it's a random measure that on balls grows at least like the radius of the ball to the right power. I'm done, eh? It's just now it's all easy, eh? So cup competitors, they give you this lower density estimate on the limit mu. Then you do cone competitors. What is a cone competitor? Is similar as before. I look at the trace over a sphere, and now rather than comparing with the cup competitors, I compare with the cone, center of the sphere towards the trace. I compare with the cones. I do this for every radius. What do I learn? I learn that this ratio is increasing. Not only is bounded from below uniformly, it's also increasing. And now we shoot the mega cannon here, okay? So there is this super cool theorem. How many measures are there for which this density, the limit of these densities exists and is positive and finite? Answer, the good ones. So it's a multiplicity times a chain restricted to a rectifiable set. This is a super famous theorem of Price, okay? And crucially used here to show that this random measure mu is not anything, is actually super cool, is a rectifiable set with a density bounded from below. Rectifiable essentially means that if you take the blow-ups of this set and you do the Hausdorff measure limit, then you go to Hn restricted to a plane. And now using this fact, using the rectifiability, using the fact that this measure blows up to a plane, okay, plus the density estimate, this means that this minimizing sequence on a ball is really look like the complement of the trace on the sphere is really like two spherical hemisphere, close and close. So it really means that this theta is going to 1. The limit is going to 1. So you can prove that then this theta is at least 1 by sort of quantitative spherical isoperimetric inequality plus what you have discovered so far. You find that this theta is larger than 1. And that's it. Because now this guy converges to a random measure mu that is larger than Hn of S for a closed set S. This is enough to prove that you are C-spanning. Why? Because if this S is not C-spanning, then there is a curve gamma that it doesn't intersect. But now a closed set doesn't intersect another closed set. then it doesn't intersect the tubular neighborhood with this curve gamma. There is space between the two. There is a positive distance. Now, mu, the measure of S inside the tubular neighborhood, is 0, but this is larger than the limit of the measures of the Sj in this tubular neighborhood. And this is super suspicious because the Sj's are C-spanning. So they intersect gamma and they intersect every homotopic copy of gamma that fiber out the tube. So by a projection argument, you can show that since they are C-spanning and they intersect every fiber, there is a small amount of area that they need to put there. It's like they have to project at least on a sort of disk. Now, it's not really a projection, so there is a Jacobian, but it's uniform in J. So 0 larger than positive, contradiction, S was C-spanning, proof is done. So CAP competitors, Almgren's existence paper for currents in higher codimension, competitors, people in the 30s proving the monotonicity of the area ratios. You can't say that this is, the proof in itself is new. The proof is, using the bag of tricks of geometric measure theory and theory of minimal surfaces, combining them in this setting. And it gives you a nice solution that doesn't require fancy compactness theorems, but it requires Price theorem. So a super cool thing that happened when De Rosa, De Filippis, Giraldini himself, and I think maybe Jonas Hirsch too was involved in one of the papers. I don't remember because it's many papers. So a very cool thing that they did, and then I'm done, when they proved this thing for higher codimension than for anisotropic integrals, is they started stripping down this proof. For example, in the anisotropic setting, you don't have the monotonicity formula. You will never discover this. So you will never use Price theorem. So how do you circumvent that? Okay? The inspiration for doing that comes from works of Guy David. Guy David with Sams were studying some uniform rectifiability. They had a nice modification of the Federer-Fleming deformation theorem. Okay? So they went picking up, again, something in the amazing bag of tricks of geometric measure theory to avoid using Price theorem and still getting away with the theorem. So this theorem is really a clever way of doing this thing, but it's really use the whole arsenal of tools, okay? So this said, now, okay, we have an existence theorem, and then tomorrow we will start wetting the fields. Okay, thank you.
Thank you, Francesco.
Questions?
But I was late, so.
Yes. With a long question.
Just one remark is that somehow people tend to forget about Reichenberg. But Reichenberg in the 60s did more or less the same that Arison and Pew did.
Yeah.
Sets and measure of sets.
Yeah.
Except the topological condition of spanning, which is more complicated. So that's an important difference. Arison and Pew topological condition is much better.
No, I think you're right.
Working
Yeah.
with just sets and measure, he did it 40 years ago.
No, you're absolutely right. You're absolutely right. So I don't remember now why we are.
I died on an accident, and somehow people tend to forget about it.
No. I think that, so you're absolutely right. So I don't remember what is wrong with Reichenberg, though, but there is something that we are not happy with. About. I will think more about.
Topological condition is really bad.
No, but that's not just that. It's not that just we don't know homology. It's more. So there is something I remember. Now I'm kind of baked. I mean, it's like, but yeah, I will. So I mean, David didn't write his paper just because, just because he didn't like Czech cohomology. So I think there is more to that. So, and Almgren was obsessed with this size minimization, not just because he didn't want to read Reichenberg's paper, which he read very carefully. So there is more to that. So but I agree with you that the idea of going, kind of old school Bezikovich viewpoint on geometric measure theory is just closed sets and measures was Reichenberg's, and he went a long way down there, I mean, with the regularity theorem and so on and so forth. But somehow for the story of the Plateau problem, there is, I don't remember which is the point, but right now, yeah, but there is something missing there, so I will find out.
You other questions? I have a small curiosity. With these results, do you expect to say a little bit more about S? So from price theory you get rectifiability,
yeah.
But maybe from a minimum result you could expect a little bit more.
Yeah, no. But once you have the existence theorem, so then you take a Lipschitz map that doesn't that is equal to the identity compactly supported in omega, and you can check that f of s is still spanning. So a Lipschitz image of a C-spanning set, it's still C-spanning. So these guys are Angre minimal sets, and so you can apply Taylor's theorem.
Okay, but in the dimension, that is dimension 2.
Yeah. No, okay. Algren minimal sets in higher dimension, not in higher codimension. In higher dimension, we know there is a theorem of Colombo, Eden, and Spolaor that's essentially saying that the top stratum is Y points. And then I don't remember how far you can go with the strata, but somehow the Y points are still there. And Algren minimal sets, two-dimensional Algren minimal sets in R4, we don't know what are the possible minimal cones. So there is a long paper, more than one long paper by students of David, where they carefully study the question. For example, when I take two planes in R4, what is the angle between them such that this configuration is Algren minimal and is not? And now I have not followed every detail of that strain of papers. But I don't think there is anything like even a characterization of all the possible ones. You can do regularity theorems like saying, if my tangent cone has some integrability properties or some extra conditions, then I can parameterize myself a la Taylor on it, C1 alpha way. However, who tells you that all the singular minimal cones will have that property? I don't know. So it's again, but it's also to be said that it's always important to keep in mind motivation. So why do you care about Algren minimal sets, two-dimensional Algren minimal sets in R7? It's less clear. While if you tell me, why do I care about minimal surfaces in two-dimensional R7 is okay. I come from a problem in geometry, I want a representative, okay. But then you have currents. So so there are several, but as a mathematical question, it's definitely very interesting and I think very open. Just what are the minimal cones, okay?
It appears somehow kind of the beginning of the story. So
Yeah.
That there are now many questions.
So what are Plateau laws? For example, For example, the boundary regularity for the Harrison cube problem, one difficulty in doing that, even if the W is a curve, is that there is no, as far as I know, but I think also Camillo and collaborators have thought about that. We don't know how to characterize all the possible boundary minimal cones for two-dimensional Algren minimal sets in R3, okay? In work in progress with Novak and Restrepo, we can do the regularity theory when W is the closure of a smooth open set. So it's like when W is a tube, which is still physically interesting because it's like the wireframe is bigger than a subfield. And the reason we can do that is because essentially we have a free boundary problem with a Young law. And essentially we can show that the only minimal cones are Y points that attach at 90 degrees on this wireframe. But we don't prove it for minimal sets. We really prove it for the minimizers in the Harrison cube problem. So yeah, it's a lot of work.
So we start with, I'm very glad to introduce Francesca Tripaldi from Leeds University. And her course, the title is on the Rham complex in Carnot groups. Thank you.
Thank you very much. So I would like to thank the organizers for inviting me. This is the first time I'm giving a mini course on this specific subject. So I would like to just say a few words of warning. So this is very little about geometric measure theory. So basically the idea is that I need to present a very technical construction in differential geometry. So there is going to be a lot of prerequisites which are rather technical and they're very algebraic. So the beginning is going to be tough and not that insightful, but there is a reason. So in the end, the idea is that in a particular geometric setting, the idea is that the Rham complex, as we will see, does not behave that well. So hopefully the aim is to give an idea of how it behaves and how the extra structure can be used to extract subcomplexes that are better suited for our purposes. So there is an aim goal, okay? So the first, especially today, is going to be tough, but I'm sorry. Okay, so so the idea is that this should be as self-contained as possible as a mini course, and the aim is to actually see an explicit example of this subcomplex, in a very specific group. So hopefully we'll get there. So the beginning is rather algebraic, okay? That's the end of my warnings. So we're gonna start by introducing, so this is gonna be rather quick as a presentation, especially today. If you don't understand anything, please stop me. So I have a Lie group, so you should all be familiar with Lie groups. So I have a differentiable manifold with a group structure. And the idea is that the group structure is a smooth map. So both, let's see. So both the group composition, the group law, this is a smooth map, and also the inverse. So this maps X to its inverse is also smooth. Why do we need this? Because we need the left and right translations to be smooth maps. So especially, this is not going to be an abelian group. So there is a very clear difference between right and left translations. And we're going to focus mostly on left translations because the literature just prefers left translations, I guess. So this is the map that we're going to use to construct a lot of things. So this is a left translation by the element G, and because this is a Lie group, this left translation map is smooth for any element G, okay? So this is the setting. So just a notation, I'm going to define this as the space of smooth sections on the tangent bundle. So this is the smooth vector fields on G. Right. One of the things I would like to present is the fact that even though we need to work on Lie groups, everything that we say is basically based on the Lie algebra. So the crucial aspect of the Lie algebras is what we rely on. So a Lie algebra is we're gonna talk about real Lie algebra, is a real vector space. And I have a bilinear map with, so this is bilinear, with two properties, which is antisymmetric. I know this seems silly, but these are both very important. So I have the antisymmetry and I have the Jacobi identity. So these are the two requirements for a Lie algebra. Especially we're gonna need the Jacobi identity after, okay? So bear in mind. Right, so the idea is that there is a special Lie algebra associated with each Lie group. And this is in particular the case when I'm working with a simply connected Lie group, which is what we're going to do. So the Lie algebra associated to a group, to a Lie group G. So we're going to denote this as Lie of G, is isomorphic as a vector space to the tangent space at the identity to G. So this is as a vector space. So we saw the Lie algebra is a vector space. So as a vector space, I can think of it as the tangent space at the identity. So E is the identity element of G. We need a bracket, okay? So this bilinear map is a bracket, is usually referred to as a bracket. So we need to define the bracket, and the best way to do this is to extend. So I'm thinking of the tangent space. I basically think of elements of this tangent space as a subspace of the vector fields, as a special subspace of vector fields. And these are referred to as left invariant vector fields of G. So left invariant vector fields of G. And so the definition for these vector fields is that, so given X just a vector field, sorry, it's in G, we say that X is left invariant if for any G, if I push forward the vector field through the left translation by G, this remains the same vector field, okay? So basically the idea is that, so made more explicitly, I have any G and any H. I have that the push, so the differential of the LG at H, this is the same as X at LG at H, okay? So basically, so this is a generalization of what you would consider as a vector basis of vector fields for R2, for example, which is dx and dy, right? And I can translate it, and it's still going to be dx, dy. That doesn't change. So in this case, I have a more complicated group law. I don't know it, but I can do exactly the same. So I take the tangent space at the origin, and then I extend the vectors by translating them through a left translation, and I keep them constant. So this is going to be the space of vector fields with constant coefficients, basically. That's the idea. So is this going to work? So does this space of left invariant vector fields then does this give me a Lie algebra, right? So basically the question is, if X and Y are left invariant vector fields, does the bracket still belong to the same space, right? And remark that I'm not going to prove. This is crucial. We're going to see the dual of this as well. The push forward through any map, any differentiable map, commutes with the brackets. So what does that mean? So if I have, basically, let's rewrite this better, sorry. So if I push forward the bracket between x and y through a left translation, so the remark tells me that this is exactly the same as pushing forward the elements inside and doing the bracket. Now, by hypothesis, both x and y are left invariant, so this is just x and y. So this is a Lie algebra, okay? So I'm very happy about this. So if I extend these vectors of the tangent space at the origin in this way, I create a Lie algebra. So basically, what am I saying here? So the space of the left invariant vector fields of G, this is an n-dimensional subspace of the space of smooth vector field, and n here is the same as the dimension of G because it's the dimension of the tangent space at the origin of G. Okay? Right. Is it? Yeah. Hopefully this is okay. So basically the idea is that given any vector v in T e G, I can construct a left invariant vector field X by imposing X at G is defined simply as I'm basically pushing forward the vector at the point G, okay? And this I can do for any G. Why am I saying this? Because I'm going to use this quite a lot in the sense that the Lie algebra of a Lie group, I can think of it in two main ways, and they're interchangeable. So I can think of them, of Lie of G as the left invariant vector fields of G with the brackets that we've seen. Or I can see this, so this would be Lie of G. This is simply TEG with the borrowed bracket from the space of smooth vector fields, okay? So why am I saying this? Because throughout the constructions that we're going to see, I'm going to use interchangeably left invariant vector fields or vectors of the Lie algebra, okay? So this is why I can do this. So this is exactly the same. I have two equivalent realizations of the same space, okay? Right, now, so the next short section is going to be about justifying why I can simply consider the Lie algebra or this space of left invariant vector fields instead of considering the group, because considering the group is a bit of a mess. So if I have, so a Lie, okay, let's see, a Lie group homomorphism. So if I have two Lie groups and I have phi, this is a Lie group homomorphism if phi is a group homomorphism and phi is smooth. So again, both G and H have a differentiable structure, so it makes sense to require smoothness. Likewise, I can consider a Lie algebra homomorphism. So a map phi from between two Lie algebras is a Lie algebra homomorphism if phi is linear and it behaves well with respect to the bracket. So phi of the bracket is exactly the same as the bracket of the images of x and y through phi. This is crucial, okay? So Lie group homomorphism and then Lie algebra homomorphism. So from a group homomorphism, to a Lie algebra. So if I have F, a Lie group homomorphism, then I know that the identity element of G needs to be mapped to the identity element of H, which means that I can consider the differential of F at the identity element, and it's gonna behave, so this is just the differential at E of G. It's gonna go from the tangent space of G at EG to the tangent space of H at E of H, right? And as we saw by the previous remark, I know that the push forward or the differential commutes with Lie brackets. So this means that I have the second, so linearity I have, because it's a differential map, and this tells me that I'm very good with the Lie bracket condition, right? So I have that this push forward gives me a Lie algebra homomorphism, right? And this, so if I start from F and I have F push forward, then this differential map is referred to as the Lie algebra homomorphism induced by F. Okay, so if I have a Lie group homomorphism down, I have a Lie algebra homomorphism up. I don't know which way you see the diagram, but yeah. So this is from F, G to H, Lie group homomorphism. I get DH, a Lie algebra homomorphism, which is the Lie algebra homomorphism induced by F. And as we've seen before, this is Lie of G and Lie of H, okay? So good, I get at least one correspondence. So the other way, so I'm not gonna prove this, but the other way holds as long as G. So the domain of this function is simply connected. And this is the case where we work. So this is good. So the statement just says that if I have G and H Lie groups with G simply connected, then given a Lie algebra homomorphism phi between Lie of G and Lie of H, then there exists a unique Lie group homomorphism phi from G to H, such that phi is actually what we expect it to be. So the push forward of the differential of small phi, okay? So this is just to say, if I'm interested in Lie group homomorphisms, it's the same, especially in our case for G simply connected. It's enough to study its differential, okay? So anything that happens at the level of the Lie algebras for the properties that you're interested in looking at is the same as looking at the properties at the level of the Lie group. So properties of the Lie algebras are perfectly reflected into properties of the Lie group and vice versa. Is it clear? I know I'm speaking very fast, but the idea is that in the same way that it's clear that I have a differential like from the Lie group to the Lie algebra, in this very simplified case of G being simply connected, I can also do the reverse, okay? So it's good enough to just look at the Lie algebra. Right. Just quickly, you might have heard of the exponential map. So this is just to give you an idea of what a Carnot group looks like. So the exponential map. So this is, you should have seen this in class. So I have any smooth manifold M, and I have a smooth vector field and a fixed point P in M. Then there exists a unique curve gamma on M such that gamma at 0 is the given P and gamma dot at T is the vector fields computed at the point gamma of T. So gamma is called the integral of x through P, and the exponential of x is simply, I'm not going to introduce any notation, we're not going to use it as much, but I have this integral curve, gamma 1 will be the exponential of this smooth vector field through P, basically. Okay, so how do I see, this simplifies a lot when I look at Lie groups. So I have the exponential map from G think of G as Lie of G. So in this case, I have that the exponential of any element x left invariant vector field now is gamma, the integral curve of x through the origin, okay? So in this case, gamma dot at t is x gamma t, and gamma 0 is the identity element, okay? So it makes sense because G, left invariant vector field, so it makes sense it's a vector field. I can do exactly the same exponential map, and I'm requiring it to go through the identity element. So in this case, a nice things, I have that for any x in G, this equation has a global solution. And actually, the integral curves, so gamma from R into G, are Lie group homomorphisms. And that helps a lot with everything that we want to do. Another thing is that X is a smooth map, and D, so the differential of the exponential map is the identity. We're going to use this to put some coordinates on our Lie groups, okay? So I have that D, so this push forward at the 0 vector. So this is the identity of G, because this map goes from G, which is T0G, to TE of G, which is also G. Right. So the exponential, so this is, I'm not going to, at the moment, I'm just saying that this is true, at least locally, right? It's going to be a global thing in our setting, but for the time being, remark. So given a basis of my Lie algebra, then the map alpha from Rn to G, that gives me T1, Tn to the exponential of T1, x1, and so on, is a diffeo between a neighborhood of 0 and a neighborhood of the identity element. What am I saying here? So if I don't require anything on G, on the Lie group, sorry, then I can use Rn, okay, as you would expect, like think of it as in charts. I would like to see this Lie group locally as an Rn, okay? I can do this locally through the exponential map. It depends on how you see this exponential map, because there are two main ways of seeing these coordinates. These are called exponential coordinates of the first kind. I could also potentially write it in this way because nobody tells me one next to and so on. They're not the same. They don't give you the same expression. It's up to you to decide which one works best for what you want to do. Because I'm interested in using the Baker-Campbell-Hausdorff formula, I'm using the first one, okay? So through the exponential map, I have these local coordinates right now. Any questions? I'm going very fast, I'm sorry. It's just I want to get rid of all the prerequisites. Yes.
The usual relation, exponential a plus b, or exponential a times.
Well, there's no. So it is, yeah, no. It's, yeah, it's very upsetting. So basically there is a choice. So there is a lot of choices that we're doing. So we're choosing left translations. We're choosing what kind of coordinates we're picking, but you can still pick them. So once we choose this one, this type of the first kind of coordinates, then I have a Baker-Campbell-Hausdorff formula. So I'm using this local, at the moment I just have a local diffeomorphism. And it would be very nice, I'm going to explain later why, to be able to express the group law of G via the brackets, because it's much easier to be given like the setting through the Lie algebra. So you're given the Lie algebra and the brackets, which ones are non-zero, and then to recover the group law from that. So the key here, is about expressing log of exp through exp of y as, so in general, if the group is not nilpotent, it's going to be an infinite sum in the iterated Lie brackets of the random two elements that I'm given. So I'm just going to give you the formula, and then we're going to see how it's used. So this, you can find it in a lot of algebra books, like it's very standard. So basically, what am I trying to say? Log, think of it as the inverse of exp. So I'm trying to get the coordinates in the Lie algebra, okay? So I'm trying to express the group law down, but in the coordinates in the Lie algebra, basically. So this is going to look like x plus y plus x bracket y divided by 2 plus xy divided by 12 minus y bracket xy divided by 12. And I think it's like x other things. But basically, it's the more you go, the greater the number of nested brackets that you're going to get, okay? And this can keep going. It really can. However, there is, and this is, at the moment, this is just a local thing that I can do. So now we're ready to see that if G is connected and simply connected, plus it's nilpotent, then the exponential map, so the thing that projects down from Lie G to G, is a global diffeo. And 2, the Baker-Campbell-Hausdorff formula holds globally. So in this, so nilpotent, for those that don't know, it's basically saying that these series of nested brackets will end at some point. So as I hopefully gotten across, I can simply define nilpotent Lie algebras. So G is nilpotent if the lower central series is finite. So the lower central series is G0, which is G. Then this includes G1, defined as G bracket G0. It includes G2, which is G bracket G1, and so on. This will end at GS, and then GS plus 1, which is 0. Okay? So if this is finite, then it makes sense that this long expression will finish at some point. Maybe not this soon, but at some point it will end. So it's much simplified. And in this case, we say that S plus 1 is the nilpotency step of G or the group, okay? So, a hint, we will be working with G connected, simply connected, nilpotent Lie groups, okay? So I have this nice exponential map. So it's a global diffeo, and I have the Baker-Campbell-Hausdorff formula. So in this case, I have a global correspondence between Rn and my group. So I have my element, my coefficients in Rn, and then I'm going to have an exponential of T1, X1 plus, and so on, because we decide to work with these coordinates. And the xi's are the basis for G. Xi's are the basis of G. So basically, why am I looking at log of x composed with x of y? Because basically, I'm saying that for any x and y in Rn, there exists a unique element that I'm going to consider as the composition law between x and y. So I have that x of this element, so xi's composed with x of the yi's xi's. This is the x of some zi's xi's. this is the composition law in the sense that I'm going to say that Z is then X composed with Y. So as you can see, this is, so if you do log of X, this will give you just the ZIs, okay? So this is where the Baker-Campbell-Hausdorff formula comes from, okay? And this is why it's useful to use these specific coordinates. So we are ready to see our first example. So it is the example that we're going to use for the mini course. So let me introduce you to the angle group. So the angle group, which I'm going to refer to as E, is a four-dimensional connected, simply connected nilpotently group so this is G. So my left invariant vector fields are spanned by x1, x2, x3, and x4, with the only non-trivial Lie brackets being x1 and x2 bracket to x3 and x1 to x3 3 bracket to x4. Okay, so you can check that this is an nilpotent group because G0 is everything. Then G1 is elements that are bracket at least of length 1, so both x3 and x4. G2 instead is the span of only x4. So this is because you can see x3 as x1, x2. And then G3, this is nothing. Okay, so this means that it's a nilpotently group of nilpotency step 3. And the group law, we need to use this weird formula. Okay, yeah.
So why such a group exists? You are saying what the property should have.
Yes. So I'm given the Lie algebra.
And there is always a group.
Yes, and then you construct the simply connected nilpotently group with that Lie algebra. Yes, yeah. So it's going to be an Rn, an R4 in this case because it's 4-dimensional. And so now we look at the group. Now we look at the group law using the Baker-Campbell-Hausdorff formula. So now we can recover the E. This, so there was a sum, right? So at the beginning there was a sum, and then there were a bracket of length 1 and 2 brackets of length 2, and then everything else fails because I don't have any more brackets. Right, so I start with x. So we said that this is x1, x2, x3, x4. You can think of this as exp of the same thing, right? And y, I see this as y1, y2, y3, y4. Okay? So now I really have to just go ahead and look at these brackets. So this is simply, so this, right. This is the bracket of, this is my life, just a lot of computations, boring computations. So 3 x4. And then you bracket this with the same thing, but with coefficients y. So basically, I need to remember blah, blah, blah. I need to remember that the only brackets that are non-trivial are x1, x2 equals x3, and x1, x3 equals x4. So if I go and try to do all the others, are gonna vanish, right? So the only non-trivial ones that I'm gonna get are x1 with x2 and x2 with x1 at the beginning to get x3. So this is x1 with y2, and then x2, x1, it's antisymmetric, so I'm gonna get a minus x2, y1 of x1, x2, plus, and then the only other one I'm going to get is 1, 3. So 1, 3, this would be 1, y3 minus x3, y1. After a while, you get the gist of it, but all the others will be 0. I mean, I can compute it, but then just the brackets is going to be 0. So this is just x1, y2 minus x2, y1, x3 plus x1, y3 minus x3, y3, y1, x4. So this is x bracket y. Now, the trick here is that I'm going to need another one to go, because I need x with xy, and then y with xy. So in this case, I'm going to have x with xy. Now, luckily, xy is much smaller than before. So this is x1, x1 plus x2, x2 plus x3, x3 plus x4, x4 with these x3 plus this x4. Again, I need to remember the only brackets are x1, x2, and I have none of this. And then I have 1 and 3. So I do have one of those. So I'm only left with one side, which is x1, with the coefficient of x3, which is x1, y2 minus x2, y1 of x1, x3. So this is x1, x1, y2 minus x2, y1, x4. Okay? And then I do the same with the y, and I just need to change the final one from x to y, because it's the same element, right? So the group, so I'm given the Lie algebra in the sense that I'm given the dimension and the bracket, and now I recover the group. And the group has a group law given by, so if I have x1, x2, x3, x4 with y1, y2, y3, y4. This is going to be the sum. So x1 plus y1, x2 plus y2, x3 plus y3, x4 plus y4. And this was the x plus y term. Then I have xy divided by 2. So then I recover, so I remember this has only x3 and x4. So this is 1 over 2 times 0, 0, x1, y2 minus x2, y1, x1, y3 minus x3, y1, plus, so this is xy divided by 2. And then I have the final bit, which is 1 over 12. So in this case, I have 0, 0, 0, x1, y2 minus x2, y1, minus 1 over 12, 0, 0, 0, y1, x1, y2 minus x2, y1. And this is the x, xy minus, it's too long, wait, y, x, y divided by 12. Yeah? So you just chuck them together. So I do it step by step, and then I need to sum them, right? So in the first two components, the group law is gonna look like an addition, right? Because I don't have anything else. But as you can see, starting from, well, I'm not gonna say step. So starting from the third component, I have something that is not linear, okay? So I have this x1, y2 minus x2, y1. And then going forward, I also have this x1, y2 minus x2, y1. So it's complicated. And also, as you can check, starting from component 3 onwards, this is where the non-commutativity comes in. So these are strictly and strongly non-commutative, okay? How much time do I have left? Oh, okay, good. Oh, we're going to see stratifications. Okay, so any questions on this? So this is just a way to say, from now on, I'm just going to consider Lie algebras. So there is no group. I mean, there is the group underneath, but once I have the Lie algebra, I have everything that I need. So we like Lie algebras for some reason. So, yeah. Ah, it's a good question. I suppose so. I don't know. Yeah. Yeah? Okay. Yeah, we do find it dimensional. It's already a mess. So. Right. Also, maybe one thing is good to mention. There is an infinite amount of nilpotent Lie algebras already in dimension 7. Okay, so there's a lot to work with. Right. Okay. So basically, so far we've seen we only work with Lie algebras, and then we consider we always know that there is going to be a simply connected nilpotent Lie group associated to my nilpotent Lie algebra, and I can recover always the group law through this Baker-Campbell-Hausdorff formula. So it's always going to be an Rn with non-commutative group law. Okay. Now, we are going to rely heavily on the structure of the Lie algebra. So, we're going to see homogeneous structures. Now, this is right. Okay, so from now on, there is no classical literature, I would say, or no classical terminology. So this is what I'm going to define as homogeneous structure, but it is borrowed from Wallenstein, if you're familiar with those terminology. I should also say that anything I've mentioned so far, there is a good book that I relied on to prepare these notes, which is, I think it's a book already. I don't know if it's out. Otherwise, the notes, Le Donne. I don't know the title. the book. Right. Okay. So now we're simply looking at the Lie algebras. So we say that. I don't know if it's a prime. Is it a primer? Yeah. Okay. Because there is. The book. I mean, you can find it also on his website. Right. Thank you. So a connected, simply connected Lie group. So we say that the Lie group, a connected, simply connected Lie group, we only work with connected, simply connected. Lie group is homogeneous if its Lie algebra admits a family of dilations. So what are dilations? So dilations, delta R, are Lie algebra morphisms of this Lie algebra that you're given. So they're the endomorphisms of the form. Now this is not exactly this, maybe the standard way of seeing this. Delta lambda, this is another exponential map, is the exponential map of matrices, maybe the one that you're more familiar with. The exponential map of a natural logarithm of lambda. So this is simply, this is the expansion. But basically, why am I seeing this in this way? So A is a diagonalizable linear operator on G with positive eigenvalues. So exp is the exponential of matrices, and ln is just the natural logarithm of lambda. Why am I seeing this in this way? Because then it makes sense to make this, to split G into the eigenvalues of this matrix, okay? So this gives a direct sum decomposition of G into eigenspaces of A. So if I have xi, which is a basis of eigenvectors of A, then in this basis, so I can see A as a matrix, and so this is, if you want to be pedantic, but the matrix ideation of A is just the diagonal matrix with a list of the eigenvalues, right? And positive eigenvalues means that each new i's is positive. So basically, why am I using the logarithm after? Because then the matrix of the dilation is just the diagonal matrix with lambda to the eigenvalues of A. Okay? Believe me, you can check it. Right, so I have basically a nice diagonal matrix, but this is kind of directly or indirectly splitting G, the Lie algebra G, into subspaces, okay? So the eigenspaces. So the eigenvalues of A are called this is going to be used so much. The weights, and I would say stress these are homogeneous weights of delta lambda, of the dilation. Then if I have a collection, so I have the collection of the weights. Now this is actually not, so this is with the with A, okay? So this is just the collection of weights. It's nothing says that necessarily each one of these weights have to be different, right? So they might have some multiplicity. So just to make things a bit quicker, I'm just measuring them without I'm just listing them without multiplicity by using p's, weights, p's. And I can also order them. We're working with real eigenvalues. Sorry, this is not n, this is s. S is less than or equal than n. So I'm just taking them with the multiplicity, I guess. So I'm just listing the different ones. So for the idea is that for each pj, so the eigenspace, so this is the eigenspace of A with eigenvalue pj, then I have that G is simply the direct sum decomposition between 1 and S. So I'm listing them, G, P, J. And if I bracket an element in G, P, I with an element in G, P, J, I end up in G, P, I plus Pj. Okay, why is this the case? It's because by assumption delta lambda is a Lie algebra homomorphism. So this means that for any x in GPI and y in GPJ, then if I delta lambda their bracket, delta lambda is a Lie algebra homomorphism. This comes in. This is the Lie algebra homomorphism. So I'm dilating by lambda to the pi of x, lambda to the pj of y, which means that this is lambda to the pi plus pj of the bracket. And so the dilation has eigenvalue pi plus pj on the bracket. Okay? So you can see this. So usually this stratification, or you've seen stratifications or gradings, you see directly the direct sum decomposition. But you can also see this as a Lie algebra homomorphism on the Lie algebra G, and that helps a lot if you want to kind of characterize the amount of homogeneous structures that you can put on a single Lie algebra. This is going to be clear with an example. But basically, first of all, this is 4. So we have this direct sum decomposition, and the fact that I have a finite amount of eigenspaces implies that this Lie algebra is nilpotent. After a while, I need to finish, okay? Right. G is homogeneous and nilpotent connected, simply connected group. Then through the exponential map, we've seen that there is any correspondence of a Lie algebra homomorphism to a Lie group homomorphism. Okay, so I can bring the dilations down to the group because I'm working with simply connected Lie groups. Okay, so this is also true, but we don't care about the Lie groups, we said. So this is a point of contention. So we say then that if the weights are positive, then we have a homogeneous structure. Homogeneous. If the weights are positive integers or can be made into positive integers, then this is a positive grading. We call this decomposition as a positive grading. So the decomposition is a positive grading. If the weights are positive integers plus the first one is equal, can be made equal to 1, and then G1 now is bracket generating, then we call the decomposition a stratification. So bracket generating just means that you can get G as the span through a bunch of brackets of elements only in, I can do this in G1, okay? So every element in the Lie algebra is a bracket of elements in G1, okay? So this means that stratification is a strong requirement. So I have that stratification is, I have a dilation whose direct sum decomposition has this first layer that is bracket generating. And it's much stronger than a positive grading, which is much stronger than homogeneous, which is much stronger than nilpotent. So what I would like to convey is that there's a lot of nilpotent Lie groups which are not homogeneous, not even homogeneous. There's a lot of homogeneous groups that are not positively gradable, and there's a lot of positively gradable that are not stratifiable, okay? So these are strict inclusions, if you want, but it doesn't mean that a stratifiable group cannot be also positively graded. And an example is the angle group. So on the angle group, I can put this dilation, so the A1 that I'm considering is 1, 1, 2, 3. And A2 that I'm considering is 1, 2, 3. Yes. Yeah, we will also only the algebras, no groups. Okay, so these look different, okay? And the eigenvectors are actually just our, like, you can take a basis of eigenvectors as the basis that we saw before. So in this case, I have that G1 is the span of x1, x2. G2 is the span of x3, and G3 is the span of x4. In this case, I have that G1 is the span of x1. Well, Gi is the span of xi. Okay. So they look very different. So even the dimensions of the eigenspaces are different, okay? So as you can see, the first choice, is much nicer because it is a stratification. Why? So G1, W1 is 1, and it is bracket generating. So I'm left outside of G1, I have x3 and x4, and they both can be seen as brackets of elements in G1. Yeah? So this is a stratification. Yay, yay, happy. The second one is nice, but it's not that nice. Because I have that W1 is 1, but this G1 is simply x1. I'm not bracket generating anything with one element. x1 bracket x1 is going to be 0, okay? So this is not bracket generating. But I have found a space of, like, a collection of eigenvalues that are positive integers. So this is actually a positive grading. So it's the next best thing, positive grading. So this decomposition is a positive grading. They are not equivalent. So there is a way of classifying these homogeneous structures. So if you can put a stratification, the group is usually referred to as stratifiable. And you don't usually care about the other homogeneous structures. So that's the preferred one, okay? How much time do I have? Oh, okay. Oh, okay. Good. I can blab on about these things. Okay, so the thing is, stratifications are very, very cool. And we like them. So it's not like, it's not a given. So the possibility of putting a homogeneous structure comes from the structure of the Lie algebra. So you have to study the Lie algebra, and in particular, you have to study what is known as the split torus of the Lie algebra. We don't care about that. But this split torus has a dimension. The dimension will give you the amount of non-equivalent homogeneous structures that you can put. And then you manually have to check if one of them is a stratification. So it's a lot of work. It's not a given. So in this case, our Engel group is stratifiable. So we can put a stratification, even though we have also positive grading that is not equivalent to that. So we are mostly, well, yeah, mostly. For this course, we are definitely just interested in stratifiable Lie groups. Again, I say groups we mean algebras. We always mean algebras. So the usual notation that I'm going to use, so far we've seen this notation. We're not going to use this notation. We are going to use V1, V2 as the subspaces. So this is fairly standard. So because it's a stratification, we already know that V1 is bracket generating, right? And it behaves well with respect to the brackets. When I say this, it just means that the dilation is a Lie algebra homomorphism, okay? So this is directly from the definition of stratification. Then another cool thing about stratifications is that the successive steps of the lower central series are in direct correspondence with these VIs, namely, so I hope I get the indices right. So the successive step quotient between GI mod GI plus 1, this is isomorphic to VI minus 1. So the idea is that G0 mod G1, yeah, this should be okay. This is isomorphic to V1, okay? So the spaces VIs are exactly the elements that are brackets of length I minus 1 exactly. Does it, yeah? Is it clear? So the delta lambdas is actually a Lie algebra automorphism. And I also have, so basically it's just saying delta lambda, as we have seen by definition, this is the bracket between delta lambda x, delta lambda y. And delta lambda inverse is simply delta by 1 over lambda. And as a matrix, the dilation has determinant lambda to the q. Now, this capital Q is a very important quantity, and this is simply 1, so the eigenvalue 1 times the dimension of V1 plus 2 times the dimension of V2, as you would expect, and so on. And this is called the homogeneous dimension of G. Of course, it depends on the homogeneous structure that you put on. If even in angle, like if you put the stratification, the homogeneous dimension is going to be different than if you put the grading, okay? But in this case, so it depends on the homogeneous structure. And it's usually, especially, so in stratification, this is always greater than n, and the topological dimension of the group or the dimension of the Lie algebra. Right. Now, the idea is that Carnot group is what we like because, well, sorry, stratifiable groups is what we like because what we're interested in looking at is sub-Riemannian geometry, okay? So So basically, the bracket generating condition will allow us to put, so the bracket generating condition allows us to put a sub-Riemannian, we're going to see what this means, sub-Riemannian structure on G that is also homogeneous. So basically, we're going to see, so in the title, there was Carnot group appeared as a name. Carnot groups, we haven't seen what sub-Riemannian means yet, but Carnot groups are basically stratifiable groups where you choose to identify the stratification, so to pick the stratification as the homogeneous and you decide to put a Riemannian structure only on the horizontal distribution, which is defined as the push forward of the first layer. So when you have a direct sum decomposition, I refer to the subspaces as layers, and I am putting a Riemannian structure only on the first layer. Okay, so if I'm on the group, I'm left translating V1. Okay. So the idea is that the bracket generating condition on V1 tells me that I can construct a nice enough metric space. So I'm going to create what is usually referred to as a CC metric, which is not going to be Riemannian, and it's sub-Riemannian in the sense that I have a Riemannian structure, but only on a sub-bundle of the whole tangent bundle. Now, next time I'm going to go a little bit more into details as to why I need the Lie bracket generating condition when it's not a course on sub-Riemannian geometry, okay? So it's just to convey the idea that stratification plus sub-Riemannian structure will create problems on the de Rham complex, okay? Good. Thank you.
I think we can start. Welcome everybody to this afternoon session. I'm very glad to introduce Professor Bertian from the Institute that we talk about rectifiability and the algebra.
So I am talking. So I want to talk about quantitative differentiability and rectifiability. And so there are some notes. So I gave a topics course on on these notions a couple of years ago, and so there are some notes on my website. If you go to cims.nyu.edu/twiddle-r-young courses. I think Q diff. You can find some notes and some resources about this. But let me start with an introduction of what I want to talk about this week. So recall that a function is differentiable. If we have a function from Rm to Rn, this is differentiable. This is differentiable if, well, there are a lot of definitions. Let's say if there, and let's say differentiable at x. There are a lot of definitions, but one way we can define this is to say that there exists some affine alpha such that near x, f can be approximated by alpha. So f of y minus f of x, minus alpha of y is bounded by some constant, by something that's smaller than the distance from y to x. So we say that f is differentiable if it can be approximated by an affine function near x. Likewise, a set E in Rm is rectifiable. Again, there are a lot of definitions that you could use, but one of them is that if for almost every x in the set, the approximate tangent plane of E near x is a plane. If for almost every x in the set, E can be approximated by a tangent plane. And both of these notions are qualitative, which means that these are yes-no notions. Either a function is differentiable at a point or it isn't. Either a set is rectifiable or it isn't. Either it has an approximate tangent plane at a point or it doesn't. So these are yes-no properties. And these are infinitesimal. And by that, I mean that they only depend on what happens in the limit as y approaches x, or in the limit as you zoom in closer and closer around E. They don't refer to a specific scale. They're infinitesimal. These properties only hold in the limit. So what I want to do this week is I want to talk about quantitative notions of differentiability and rectifiability. Instead of notions that are yes or no, I want to talk about, well, this is sort of epsilon differentiable. This is close to an affine function. And instead of talking about notions that hold at infinitesimal scales, notions that only hold in the limit, I want to talk about notions that hold at specific scales. So I want to talk about, can you say that a function can be approximated by a affine function up to an error epsilon on scale delta, say. So just to give you a prototype of what I want to talk about. So a standard theorem in about differentiability is Rademacher's theorem. Rademacher's theorem says that if f from Rm to Rn is Lipschitz, then f is differentiable almost everywhere. Again, this is, you know, this is an infinitesimal notion, and it's an almost everywhere notion. It's a yes/no notion, and it's an infinitesimal notion. How could we make this quantitative? Well, one thing we can do is this. We can define, we can say that f is, say, epsilon differentiable at some point x if it can be approximated by an affine function up to error epsilon. So if there exists some affine function Rm to Rn such that the distance between f of x and alpha of x, let's say, sorry, where's the eraser? Sorry, I missed a step in the definition. So I don't want to say at a point, I want to say on a ball. So on a ball, say the ball of radius r around x, if there exists alpha, such that for every point in that ball, the function can be approximated f of y minus alpha of y is less than epsilon times the radius of the ball. Right, so this is a local notion now because it's talking about the behavior of the function on a ball of radius r, and it's a quantitative notion. It's no longer yes or no, it's what epsilon can you choose here? How small can you make epsilon? And then what's a quantitative analog of Rademacher's theorem? Well, a quantitative version would tell us about how frequently this property holds. Yeah.
And this for all y that are in the ball.
Oh yeah, yeah, for all y in the ball of radius r around x. Yeah. So a quantitative notion. Let me move this up a little. A quantitative version of the theorem would tell us about how often this property holds. So one version of a quantitative theorem would be to say that for most balls, let's say if f is, let's pick the Lipschitz constant, say 1 Lipschitz, then f is epsilon, then for every epsilon greater than 0, f is epsilon differentiable on most balls. Right, and part of what I want to do today is, you know, state this more formally, but just for the sake of an introduction, this is the sort of thing I'm looking for. If f is a 1 Lipschitz function, then it is close to an affine function on most balls according to some appropriate measure. Does this make sense? Okay, and so we can ask, okay, why are we interested? What does this help us do? Like, why is this? So the goal for this week is to state and prove theorems like this and apply these to studying geometry and analysis. Okay. So why are we interested in having theorems like this? Why are we interested in this sort of quantitative theorem? And like I said, if you're coming in late, you can find some notes and other resources on my website. So why are we interested in proving theorems like this? Well, there are a couple of reasons. There are a couple of things we can use this for. One, this is really helpful for studying coarse geometry. If coarse geometry and geometric group theory, when we're not interested necessarily in a space, in a manifold, when we're interested in talking about collections of points and countable metric spaces or discrete groups, this is really helpful for dealing with coarse geometry because, for instance, if I look at, say, instead of talking about a function from Rm to Rn, if I want to talk about a function from Zm to Rn, the integer lattice, well, how can we study the differentiability of a function like this? Well, certainly we could say on the qualitative infinitesimal side, we could certainly say, okay, approximate f, or in this case, f is only defined on the integers, so we can extend f to the rest of the domain, to all of Rm. Then the extension is differentiable almost everywhere. Right, because you can extend it to a piecewise linear function, and a piecewise linear function is certainly differentiable almost everywhere. The problem is that that sort of differentiability doesn't tell you anything about the original function. It doesn't tell you about what you want to know, which is how does this function behave. If you want to know something about the original function, you really do need something like this, because from the course point of view, from the quantitative point of view, if you have some version of this theorem, if you can say that a one Lipschitz function is epsilon differentiable on most balls, then you can find many balls, including large balls, where f is epsilon differentiable. And so then you can say, okay, if I have a one Lipschitz function from Zm to Rn, then I can find some ball, maybe that ball is, radius 1,000, radius 1,000,000, radius 10 million, on which the function is close to affine. And you're never going to see that from the infinitesimal point of view. You're only going to see that from some sort of quantitative point of view. Is okay? So one application is we can use this for coarse geometry. What else can we do? This has some nice stability under limits. It's easy to construct, it's easy to construct Fi from Rm to Rn such that each of the Fi's are differentiable. But the limit of the Fi's is not differentiable, right? It's easy to construct examples like this. It's easy to construct examples like this. You can even do this, oops. You can even do this when f and when all of these functions are uniformly Lipschitz. Even if the Lipschitz constant of all these Fi's is finite. And sort of the reason for that is because, well, you can have, one function which is like, the reason for that is basically scales. You can have a function that looks like one thing at one scale, and then if you zoom in near the center, maybe it looks a little different at that scale, and if you zoom in the center there, maybe it looks a little different at that scale, and so on and so forth. And so it's easy to construct a sequence of functions that starts out nice and flat, and then you add a bump in the middle, and then you add another bump in the middle of that, and so on and so forth, until you get in the limit, you get a function which fails to be differentiable at that limit point. And this happens exactly because the notion of differentiability doesn't have a scale built in. All you know from differentiability is that as you zoom in further and further, the function flattens out. if you have a sequence of functions, it could take those functions longer and longer to flatten out, right? But if you have a sequence of functions that are all epsilon differentiable on the same ball, if these are all epsilon differentiable on the same ball, then so is the limit. So we can use this to get, we can use these definitions to get some nice stability under limits. And the last application is something that maybe I'm going to try to talk about like Thursday or Friday. It gives us a way of looking at complicated functions and building them up out of simpler pieces. It gives us, I really like the point of view that these sort of quantitative arguments have that lets you take some complicated object and break it down into a bunch of simpler objects. So I'll try to. It's going to be a little bit fuzzy now, but I'll try to explain that a little bit more as we go on. And so I should credit this a lot of this viewpoint is inspired by a bunch of other mathematicians, including so a lot of this is inspired by work of Eskin, Fisher, and White, by work of Jeff Cheeger, on the analysis side, work of Jones, work of Doran Soro, work of David and Sems. And you can find, like I said, you can find links to a lot of the relevant papers on my website. So, is this okay so far? Any questions about any of this so far? So today, what I want to do is I want to start with the simplest case of this. I want to talk about, even Rademacher is a little bit complicated because of the multiple dimensions. So I want to talk about quantitative Lebesgue's theorem. So just the one-dimensional case, a Lipschitz function R to R is differentiable almost everywhere. And so if we want to take, so Lebesgue's theorem says that a Lipschitz function from R to R is differentiable almost everywhere. If we want to make this quantitative, then again, it should look like the theorem we wrote there. F is epsilon differentiable on most balls. In this case, I guess because we're in one dimension, I mean we mean that's epsilon differentiable on most intervals. So let me start by defining what it means most here, by defining what I mean by most intervals. So here's what I'm actually going to talk about. So this is also called the weak geometric lemma, or at least this is a version of the weak geometric lemma. Let d epsilon be the set of points x comma r, where f is not epsilon differentiable on the ball of radius r around x. But we're on the real line here, so just the interval from x minus r to x plus r. Right? If f is epsilon differentiable on most intervals, then this set ought to be small. And so we can define that by saying that for all epsilon greater than 0, this set is what's called a Carlson set. And by that I mean that for every y and s, we have that the measure with respect to the measure of this set of points where it fails to be differentiable with y minus s to y plus s across the interval from 0 to s. This measure is, one more parenthesis, this measure is less than or equal, is less than s times some constant depending on epsilon. Right? Is this notation okay? Another way to write this, is just to write this as a double integral. This is the integral from 0 to s, integral from, sorry, sorry, which one? Give me just a sec. Yeah. Okay. So integral from 0 to s, integral from y minus s to y plus s of the characteristic function of d epsilon at x comma r integrated with respect to dx dr over r. Right. Is this definition clear? So what does this mean? How can we think about this? Well, like I said, the idea of this is that this says that most intervals are not in this set. This says that f is this ought to say that intervals like this are rare. What does that mean? There are a couple of ways to interpret this. One is to say this. Oops, not dr over dr, dr over r. One way to think about this is this measure, dr over r, is a measure on scales. This is the measure on the radius of an interval. And the way that measure works is that the measure of an interval from a to b is log of b over a. Right? So when we say that this set has measure less than s times a constant times epsilon, or if we say that this integral is less than s times a constant times epsilon, one way to think about this is we can define, let's call it kappa epsilon of a point and a radius. We could define kappa epsilon is the measure with respect to dr over r of the collection of radii such that r is less than rho and xr is in d epsilon. Right? We could define this function, and what this function measures is essentially the number of scales such that, and really these are scales less than delta, less than rho, such that f is not epsilon differentiable on the interval from x minus r to x plus r. Right, so this is sort of a measure of how bad f is near x. Right, this is sort of a measure of how many scales there are where f has like a corner at x, or where f oscillates near x. or where f does something very strange, where versus scales where f is epsilon close to a straight line near x. So you know, the bigger this is, the worse f is near x. If this is small, then f is pretty decent near x. And so what this says is that the integral from y minus s to y plus s of kappa epsilon this says that this is less than a constant times s. So on average, kappa epsilon is less than some constant depending only on epsilon on average. So when I say that that this applies to most intervals, I mean, well, one of the things that means is that for a generic point, if you look at all the scales below scale s, and there are infinitely many scales below scale s, because you know this dr over r integral counts s and s over 2 and s over 4, s over 8, counts all of these about the same. Out of these infinitely many scales, there are only finitely many of them. In fact, a finite number bounded by a function of epsilon. There are only finitely many of these where the function fails to be differentiable, fails to be epsilon differentiable on that interval. So it's rare in that sense that for almost every point, this is finite. And furthermore, if you take this function and you average this over the interval from y minus s to y plus s, the average is going to be less than a constant times epsilon. Is this okay so far? Okay. So this is one way of looking at this. Another way to think about this. I mean, we're integrating over a slightly strange object here. We're integrating we're integrating this characteristic function where x ranges from y minus s to y plus s, and r ranges from 0 to s. Another way to think about this is that this set that we're integrating over corresponds to subintervals of the interval from y minus s to y plus s. This is not exact, right? Because what are we doing here? We're taking here, we have the interval from y minus s to y plus s. We're taking a random point here and a random radius around that point. You know, there's every possibility that that random radius could contain, could go past one endpoint, could go past the other endpoint. But that's rare in this, but that's rare. And what I mean by that is that that is a finite part of this measure. I mean that that dx cross dr over r, the measure of this rectangular region the measure of this rectangular region minus the intervals that are genuinely subintervals of y minus s to y plus s. This has finite measure. In fact, this has measure bounded by some constant times s. And so if we can say, you know, so another way of thinking about this is that if we look at all of the subintervals of y minus s to y plus s, then this measure assigns that set of all the, sorry. What was I? So another way of thinking about this is that if you don't like this integral, we're integrating from 0 to s and y minus s to y plus s, you can replace this integral with the integral over all subintervals of y minus s to y plus s. And if you do that, the only change is that maybe you have to change this constant depending on epsilon.
Just a question, f is just Lipschitz, right, for the theorem?
Yeah, so here we have f, is 1 Lipschitz. It's okay. Any questions about any of this so far? So let me show you an example. Let me show you 2 examples, really. So for example, let's take a function f of x equals norm of x, right? This is a function where the graph is like this, right? So in this case, what does it mean for this function to be epsilon differentiable on an interval? Well, certainly if I take an interval that doesn't contain 0, well, the function is exactly linear on that interval. So if I have some interval that does not contain 0, then f is, well, it's not just epsilon differentiable, it's affine on that interval. On the other hand, if I have an interval that does contain 0, then on that interval, you can't really approximate f by an affine function, right? So I guess what I really want to say is that, you know, if 0 is in the middle of this interval, one way of saying that is to write if 0 is contained in, let's call it 1/2 I, where so the idea of this notation is that if I have a ball, if I have a ball of radius r around x, then 1/2 of b is the ball of radius r over 2 around x, right? So if 0 is contained in, if 0 lies in the middle half of the interval, then f is not, say, 1/10 differentiable on I, right? So if I have intervals that avoid the origin, then those are okay, the function is affine. If I have intervals where the middle of the interval contains the origin, then function is not affine. So if we think about how many scales does f fail to be epsilon differentiable at that scale, well, technically speaking, you know, if I take the origin, then at every scale around the origin, if I take any interval centered at the origin, I get the same function, or I get a scaling of the same function. Our f is not epsilon differentiable on any of those neighborhoods around the origin. And similarly, if I take a point, you know, say this is x equals 5, then sure, f is affine on small intervals around x equals 5, but as soon as I get to, you know, intervals of radius 10 or 15 or 20 or 100, I'm back in the same situation. If I take really large intervals, this again fails to be epsilon differentiable. So technically speaking, you know, f is not epsilon differentiable at infinitely many scales around any point, but this is why we have this condition. This is why we're integrating over subintervals of a given interval to avoid exactly this. F is not differentiable on large scales, but when we take this integral, and when we integrate over these subintervals of a given interval, we're focusing on the small scales mostly. So even though f is not differentiable at very large scales, it still satisfies this theorem. Basically because if I take any interval, let me clean this up a little bit. If I take any interval, f is differentiable, f is epsilon differentiable on most subintervals of that interval. If that interval doesn't contain the origin, then it's affine on every subinterval of that interval. If that interval does contain the origin, well, there are some subintervals where it fails to be differentiable, but when we say most subintervals, what that means is essentially pick a point, pick a scale around that point where it's equally likely to pick, you know, scale 1 or scale 1/2 or scale 1/4 or scale 1/8, scale 1/16. Most of those scales are very small, so most of the time if I pick a random point and I pick a random scale around that point, that scale is small enough that the corresponding interval does not contain the origin. So some points are very bad. Any interval of the form f is not epsilon differentiable on any interval around 0. But on average, if I pick an s, if I pick an s and a y, if I pick some any particular interval, then if I pick a random point inside that interval, the function is going to be good. The function is going to be epsilon differentiable at all except finitely many points, finitely many scales around that point. Is this okay? Yeah?
What the dependence of C epsilon is on the function?
No, it's just on epsilon.
Just on, so it's
yeah.
Some universal function of epsilon?
Yeah. It's you know, it's not a very nice function of epsilon. It's like, you know, epsilon to the -1/epsilon or something, but you know. More questions? Okay. So it's okay to have some very bad points. You just can't have too many really bad points. Likewise, let's take a different function. Let's take f of x equals, say, sine x, right? So this is a function that looks like this. And we can ask, again, okay, where is f going to be epsilon differentiable? What intervals can we find where the function is close to affine on those intervals? Well, on one hand, if I take a point here, and I take a sufficiently small interval around that point, then the function is close to affine. And the scale I need there is going to have to do with the second derivative of the function. But you know, this is the sine function, so the second derivative is bounded between -1 and 1. So you know, if the length of I is less than about root epsilon, then f is approximately epsilon differentiable on I. So if I have a very small interval, it's epsilon differentiable. But also, if I have a sufficiently big interval, it's also epsilon differentiable. Because if I take a sufficiently big interval, remember, to be epsilon differentiable, I need that f minus my affine function is bounded by epsilon times the scale of the interval. So, well, if I take my affine function to be 0, this is bounded by, this is at most 1, And so if the scale of the interval is large enough, then again, f is epsilon differentiable. Did I get that right? This is because I think maybe I don't need the square root here. Maybe I need this to be actually epsilon. Anyway, either way. But in any case, my point is that at very small scales, this function is epsilon differentiable, and at very large scales, this function is epsilon differentiable. And that's more or less independent of what your starting point is. No matter what x you choose, if you take a ball of radius epsilon around x, then function is epsilon differentiable. If you take a ball of radius 1 over epsilon around x, then f is epsilon differentiable. And so this d epsilon is roughly the set of points of the form x comma r, where r is bigger than epsilon and smaller than epsilon inverse. That means that this function kappa epsilon that measures the number of scales less than rho, where this function is fails to be epsilon differentiable, that means that this is less than or equal to the log of epsilon inverse over epsilon is, what is that? That's 2 log epsilon. So you can compute this integral, or you can compute the average of this function, and you can see that in the sense of Carlson sets, f is epsilon differentiable on most intervals. Okay? So this is what we mean. This is what we mean by most intervals. We mean that the set of intervals where this condition fails forms a Carlson set, forms a set that satisfies bounds like this. Is this okay so far? Okay. So one thing that's important here, one thing to keep in mind, is that all of this is scale invariant. These definitions are all scale invariant. Right. In the sense that if f satisfies the theorem, so does if I rescale f. So let's define, say, f 1000 is, let's blow this up by a factor of 1000. So that's 1000 f of x over 1000. So if f satisfies this, then so does the function you get by blowing f up by a factor of 1000. So does the function you get by shrinking down f by a factor of 1000. Because what happens when you apply this scaling? Well, here our original f, if f of x equals sine x, then it's differentiable on scales less than epsilon and scales bigger than epsilon inverse. If we rescale, that's just going to multiply those scales by a factor of 1000, say. If we rescale by a factor of 1000 like this, it's going to be differential on scales less than 1000 epsilon, bigger than 1000 epsilon inverse. And we get the same, because this measure only relies on the ratio between those two scales, multiplying everything by 1000 isn't going to change the ratio. It isn't going to change this measure. So so all of this is meant to be scale invariant. If you take a function and you blow it up or you shrink it down, it should satisfy the same inequalities with the same bounds. It's okay? Okay. So that's the idea of the theorem. That's what I want to show. So now let's try to prove this. Excuse me. And what I like about these theorems is that the proofs are often very concrete, are often very geometric. For instance, here we can prove this quantitative version of Lebesgue's theorem just by using lengths. So remember the setup. Let's let F be 1 Lipschitz. I'm going to define an auxiliary function f bar. This is going to be the graph of f. So this is the function f bar of x is equal to x f of x. So this is just the graph of f. Because this is just the graph of f, and because f is 1 Lipschitz, then f bar is root 2 Lipschitz. And and what we're going to use about that is that therefore the length of the segment, the length of any segment of the graph is at most root 2 times the length of the corresponding interval. Right? So let me see if I can, let me switch pens, see whether one of these is a little darker. So, like I said, we can prove this theorem essentially relying just on the length and the Pythagorean theorem. And so here's what we're going to do. So for, sorry, I should have, this is the problem with whiteboards. Never mind. Okay, I'm just going to stick with this color. For k greater than or equal to 0, let me define L sub k of an interval, and let's say the interval from a to b is the sum from I equals 0 to 2k minus 1, 2 to the k minus 1, of the difference between f bar of a plus I over 2 to the k times b minus a minus f bar of a plus I plus 1 over 2 to the k times b minus a. I shouldn't have let that stretch out quite so long. The idea of this is that, well, L0 is just, we're summing over one term, and that term is the length of the line segment from f bar a to f bar b. So this is L0. L1, we take that interval, we split it in half, and we add up this length plus this length. It's going to be L1. L2, we split the interval again into halves, into quarters, to get L2, and so on and so forth. So as k increases, that corresponds to taking this interval and dividing it into more and more segments, just cutting those segments in half over and over again. Now, there are a couple of things we can state about this. So, one, each of these LKs, LKI is less than or equal to square root of 2 times the length of I, right? Because this function is, its function is root 2 Lipschitz. So no matter how many intervals I divide this segment of the curve into, the length of these line segments is going to be less than root 2 times b minus a. So that's 1. 2, the length, LKI, is non-decreasing in k, because every time I do one of these subdivisions, the length can only go up. By the triangle inequality, every time I subdivide one of these intervals, the length can only increase or stay the same. And then for the third, if I have good enough bounds on LK, then they imply the differentiability that I'm after. There exists d greater than 0, there exists a delta greater than 0, such that if L sub d of I minus L naught of I is sufficiently small, and everything has to be scale invariant, so sufficiently small means less than delta times the length of I, then F is epsilon differentiable on I. So I guess really I should say, for all epsilon greater than 0, there exists such a delta. And like I said, and this just uses the Pythagorean theorem. Because if F fails to be epsilon differentiable on I, well, the length of I is this distance here. If F fails to be epsilon differentiable on I, then that means that there's some point between f of A and f of B that leaves, I can approximate by this by the affine, by the straight line from f bar A to f bar B, from f of A to f of B. If this fails to be epsilon differentiable on this segment, then there's some point like this that leaves the epsilon normi neighborhood, right? And then by the Pythagorean theorem, if I have this curve, then any curve that goes from here to here to here, the length of this curve has to be at least epsilon square bigger than the length of this curve. If I have a triangle like this, where the distance from one vertex to the opposite side is large, then the length of two sides of the triangle has to be larger than the length of one side of the triangle. Is this okay so far? The reason I say that this is the Pythagorean theorem is because, say I have a curve of, say I have a line segment of length L, say I have some point here, which is epsilon L away, then what are the lengths of this and this? You can do a theorem with the you can do a calculation with the Pythagorean theorem to say that this length from here to here is at least 1 plus, I don't know whether it's like epsilon, I don't know whether it's epsilon square or epsilon square over 2 times L, right? So here, what do we need to, how do we choose this D and this delta? Well, this delta is going to be something like epsilon squared. And then the reason we need to choose, the reason we need to choose a large enough D is because LD only detects what the function does at A and A plus, and at 2 to the D evenly spaced points from A to B. And so, you could have a function which is, all those evenly spaced points are along a line, but then the function oscillates between those points. And so D has to be large enough to rule that out, which is about, the log of epsilon squared, say. Okay? But so this is what we need to know. We need to know that the length LK is always less than or equal to root 2 times the length of the interval. LK of I is non-decreasing in K. And if LKI or if LDI is close enough to L0I, then F is epsilon differentiable on that interval. Okay? Once we know that, we can get the bounds that we want essentially by a telescoping argument. So this is the property that we're interested in. If we can show that most intervals satisfy this property, then that would mean that most intervals F is epsilon differentiable on. And so let's define gamma of I is this difference is LDI minus L0I normalized by I, the length of I. So if gamma I is less than delta, then F is epsilon differentiable on I. And then I want to bound the number of intervals where this is bigger than delta. So here's what we're going to do. I claim that this is less than delta on most subintervals. So let's fix some interval I, and let's let, for every I and j, let's let I sub I comma j be one of the dyadic intervals that you get by cutting I in half and in half and half and half, by cutting I into halves over and over again. So let's say I is the interval from A to B, and then the jth dyadic interval at scale 2 to the minus I is going to be the interval from A plus, what is this, I over 2 to the, or j over 2 to the I times B minus A to A plus j plus 1 over 2 to the I B minus A. So we're just naming all the intervals that show up here. Then on one hand, this difference well, L sub d is just the sum from j equals 0 to the I minus 1 of the length of, oh, did I not, sorry, a sec. Right, so then we can write these differences we're interested in. How do I want to say this? Then the difference between LKDI and L naught I can be written as a telescoping sum. This is the sum from I equals 0 to k minus 1 of L I plus 1 times d I minus L I d of I. But what are each of these differences here? Well, each of those differences here, if I want to look at L I plus 1 d of I minus L I d of I, what is this? Well, we're taking our function and dividing it into dividing into 2 to the id subintervals versus 2 to the I plus 1d subintervals. Equivalently, we're taking our function and we're subdividing it into, say, 2 to the id intervals. And then we're comparing that to what you get by taking each of those 2 to the id intervals and subdividing each of those into another 2 to the d intervals, right? We're taking, so what that means is that this difference is the sum from sum over these 2 to the id intervals, so from j equals 0 to 2 to the id minus 1 of the difference between the subdivided interval, so this is the jth interval at scale 2 to the minus ID. The difference between subdividing that into 2 to the d subintervals and just taking that whole. But this we can rewrite in terms of gamma. This is the sum from j equals 0 to 2 to the id minus 1 of gamma of idj times norm the length of that interval. And so we can take this difference and write it as a telescoping sum. The difference between LKDI and L0I is the sum of these sums over all I. So we can write it as a sum essentially from I equals 0 to k minus 1 of the sum from j equals 0 to 2 to the id minus 1 of gamma idj times the length of idj. And this difference, well, this sum, these lengths are non-decreasing in k. So this is larger than this, and this is less than or equal to √2 times the length of I. So we can break up the entire length of the curve into a bunch of little terms like this. One term for every interval in one of these subdivisions. You know, we take the whole curve, and then we divide that into 2 to the d steps, and then we divide each of those into 2 to the d steps, and we divide each of those into 2 to the d steps. Each of those intervals, those are these intervals idj. Each of those contributes something to this sum corresponding to the value of gamma, and that total ends up being less than or equal to √2 times I. It's okay so far? So now this, I claim, is a sort of discrete analog of the Carlson condition. What I mean by that, oh, am I supposed to be done? What time is it? Oh, shoot, I'm supposed to be done.
Oh, so 25 minutes. Yeah, 25. Until 4.
Oh, did we start? Oh, we started at 2:30. Oh, sorry. Okay. Okay, sorry. Okay. So I claim that this is a discrete analog of the Carlson condition. Because if it weren't for this gamma term, if it weren't for this gamma, if we were just adding up, the sum over I equals 0 to k minus 1, the sum over from j equals 0 to the id minus 1. Well, first, if this inequality holds for all I, or if this inequality holds for all k, then we may as well let k go to infinity. We may as well sum from 0 to infinity here. And then if we ignore this gamma, if we just sum up idj, well, the idj's, if we fix I and we let j vary from 0 to 2 to the id minus 1, these just subdivide I into 2 to the id intervals. So if we sum up all of these, this is just the sum from I equals 0 to infinity of the norm of I, and this is infinite. So if we ignore gamma entirely, this is an infinite sum. if we multiply each of the terms by the corresponding value of gamma, this becomes a finite sum. And so that means that gamma has to be small most of the time. And exactly quantifying that is just Chebyshev's inequality. In particular, if we were to sum over all the I and j such that gamma of, if we were to sum over all the I and j so that gamma of the interval idj is bigger than delta, if instead of summing over all I and j, if we just sum over the I and j where gamma idj is bigger than delta, then, well, this is certainly bigger than that same sum where we replace gamma by delta. But this is less than or equal to the sum over all I and j. And this sum over all I and j is at most root 2 times the length of I. So the total length of all of the intervals where gamma I idj is bigger than delta, the total length of all the intervals where gamma is bigger than delta is less than or equal to root 2 times the length of I times delta inverse. So out of all of these infinitely many intervals with infinite total length, only a finite amount of that length consists of intervals where delta is bigger, or gamma is bigger than delta. It's okay? So this is so like I said, this is a discrete Carlson condition in the sense that it is saying not that not that most subintervals of I have this property. This says that this discrete set of subintervals that you get by taking I and then subdividing into 2 to the d pieces and then subdividing each of those into 2 to the d pieces and so on and so forth. Most of those intervals have this property. Most of those intervals have this epsilon differentiability property. And then we can pass from the discrete inequality to the continuous inequality by changing our starting interval. So first, is this clear? I feel like I'm a bit jet lagged. I think I'm losing a little bit of coherence as the day goes on. But is this clear enough? Okay. Let's save that. So now we want to go from this discrete inequality to the continuous inequality that we started with. And here's where we use the scale invariance. So this is true for every starting interval I. For every starting interval I, we have this discrete Carlson condition. And so we can get the continuous condition by integrating over all the possible starting intervals. Well, actually, we don't need to integrate over every possible starting interval because, well, this gives us an inequality that holds for our original interval plus, all of the ways of dividing it into 2 to the d steps and dividing each of those into 2 to the d steps and so on and so forth. So if I consider this interval plus all the intervals of length up to 2 to the d times the length of this interval, then that's going to give me all of the lengths, right? This inequality tells me about a discrete set of lengths ranging from length of I, 2 to the minus d, length of I, 2 to the 2d, I guess, yeah, dot, 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 up to 2 to the id, 2 to the minus id times the length of I. So if I vary the length of I by a factor of 2 to the d, that will cover all the different lengths. Furthermore, so let's fix let's fix a starting interval from -1 to 1. So if this goes from -1 to 1, I don't want to just see these intervals that start at evenly spaced points. I want to see all of the intervals between -1 and 1. So how can I get all the intervals between -1 and 1? Well, what I can do is I can take this picture and I can translate it up to distance 2 one way, up to distance 2 the other way. And if I do that, that'll take each of these intervals and translate it from distance -2 over here all the way up to distance 2 over here. It'll take each of these intervals and translate it over, well, over an interval containing the interval from -1 to 1. There is going to be some double counting there because, I'm going to, if I take this interval and I translate it by this much or this much or this much or this much or this much, I'm going to see one of those other intervals again. So we need to keep track of that. But if we do that, if we let the starting interval vary from length 2 up to length 2 to the d plus 1, and if we let the center vary from -1 to 1 or -2 to 2, then we'll see every interval that we care about. So let's do that. So let's fix I to be the interval from -1 to 1. Then if we look, we can define C is the interval from scale 2 to the minus d up to 1 of the interval from -2 to 2 of this sum, the sum over I and j, such that gamma of, let's take the interval that goes from y minus s to y plus s, and then do this dyadic subdivision, and sum up over all the intervals where this is bigger than delta. Times the length of that interval we're looking at. Well, and I'm going to add, just to get this to normalize nicely, I'm going to add a 1 over s over here. And we're going to integrate that from dy as y ranges from -2 to 2, as s ranges from 2 to the minus d to 1 with respect to ds over s. The discrete Carlson condition tells us that for each starting interval, for each y and s, this sum is at most √2 times the length from y minus s to y plus s times delta inverse. So this is integral from this is bounded by the integral from 2 to the minus d to 1, integral from -2 to 2 of 1 over s times √2 times the length of this interval times delta inverse with respect to dy, ds over s. This and this cancel. And so this is bounded by, well, now we're just integrating, we just integrate this, and what we get is a constant times d times delta inverse, right? So on one hand, this double integral, this sum is bounded by a constant depending on d and delta. And d and delta, remember, just depend on, d and delta just depend on epsilon. On the other hand, if we take this double integral, what intervals do we count? Well, let's evaluate. So if we let d epsilon, like we did before, this is a set of x and r such that f is not epsilon differentiable on the interval from minus r to r. Then you can write that c is greater than or equal to some constant times. Well, so first, right. Sorry. Okay. So what do I want to do? I want to say that this is. I want to say that this catches every interval. So first, I want to write this in terms of. So first, I can say that this is greater than or equal to the interval from 2 to the minus d to 1, the integral from minus 2 to 2, 1 over s times the sum over I and j. In order for this to be greater than delta, that means the function is not epsilon differentiable on that interval. So I can write this as the sum of the characteristic function of d epsilon over a bunch of points. What is that bunch of points? Well, I want this to be the sum. I want to take the sum over I and j of the points, the centers, and the radii corresponding to these evenly spaced intervals in between y minus s and y plus s. So if I take this interval, the jth subinterval here, then the center of that is going to be at some point y plus tij, and the radius is going to be 2 to the minus id, where those tij's are evenly spaced in the interval from minus 1 to 1. And we're integrating all of this with respect to dy ds over s. But then if I, oops, and there's an s here. But then if I fix s and I let y vary from minus 2 to 2, then y plus tij, tij is some point between minus 1 and 1, y plus ti over tij is going to sweep out every point between minus 1 and 1, plus some extra stuff around the edges. So I can write this. This is the integral from scale 2 to the minus d to 1 of the integral from minus 1 to 1 of 1 over s sum over I. Each term over here is going to sweep out everything between minus 1 and 1. There are 2 to the id such terms. So we can rewrite this as 2 to the id times this characteristic function. 2 to the minus id times s. Dy ds over s.
Sorry, why this is the lower bound for the length of the interval? You are bounding from below the length of this y minus s with the indicator. That's what you're doing.
I am. Oh shoot! Did I drop the? I dropped the length. I dropped the length term. That's what happened. Yeah. So there is a. In fact, there is a 2 to the 2 to the minus id. Yeah, because that's good because I am going to want to cancel this out in just a moment. Yeah. So yeah. I dropped the length term. Right. So there's the length term, and when we put that length term back in. then that magically cancels out this term here and this term here. And what we're left with is the integral from 2 to the minus d to 1 of the integral from minus 1 to 1 of this dy ds over s. But by a change of variables, now if we let s prime equal 2 to the minus id s, then we get this is greater than or equal to the sum to the integral from 0 to 1 of the integral from minus 1 to 1 of the characteristic function of dE evaluated at ys dy ds over s. So we can so we get the discrete version of the Carlson inequality by using lengths and by using the Pythagorean theorem, and that gives us a bound on these dyadic subintervals, and then we integrate that discrete bound over all possible starting intervals to get a continuous bound, to get the original Carlson inequality you wanted, to show that this integral is bounded by a constant depending on epsilon. Is this okay so far? Okay, sorry. So that's a lot of stuff to take in, I guess. But the upshot of all this, the idea behind all of this, is that we can use the length of a curve as what's called a coercive quantity. The upshot of all of this the upshot of all of this is this idea that the length of the graph of f is what we call a coercive quantity. That means that it's finite. The length of the graph of f is finite. That means that we can break up the length of the graph of f, can be written as a sum of local contributions. In the sense that if I have a curve, if I have a curve from A to B, then I can approximate it at finer and finer scales by subdividing that curve into finer and finer pieces. And then I can write the total length of that curve in a sort of telescoping series way. I can say the length of the curve is the length of this first segment plus the difference, the extra length that you get from breaking that into 2, plus the length that you get by breaking that into 2, plus the length that you get by breaking each of those into 2, and so on and so forth. I can break down the length into a sum of local contributions, and furthermore, if the local contributions are small, that forces linearity. That forces some geometric condition. And so if you have a situation like this where you can define some quantity like the length that can be written as a sum of local contributions, well, there are infinitely many local contributions making up that sum because you can keep on subdividing infinitely many times. So there are infinitely many contributions to this sum. If that sum is bounded, if that sum is finite, then most of those contributions have to be very small. And if most of the contributions are very small, then you can use that to force linearity. And so this is the basic idea, that if this didn't hold, if you had a function which was not epsilon differentiable on most subintervals, then, well, what would the graph of that function look like? It would have to be epsilon away from a line at that scale, and then another epsilon away from a line at that scale, and then another epsilon away from a line at some other scale. Every time you go down a scale, the length gets a little longer and a little longer and a little longer, and then because there are infinitely many scales, the length would have to blow up. And so the fact that that doesn't happen, the fact that your function is Lipschitz, forces linearity at most points and most scales. It's okay so far? Okay, next time. Yeah, I think so. So this is kind of our starting point, saying that a function from R to R is differentiable on most intervals at most scales. Next time we'll try to generalize this to other domains and other target spaces.
Thank you. Questions?
Is it Lipschitz or finite length that matters here? So this is so one way to generalize this is to talk about, instead of a Lipschitz function, to talk about a rectifiable set. And so you know, so instead of the graph of a Lipschitz function, you want to talk about some rectifiable set. And then it's still true that so that's sort of the something I'll get to Thursday or Friday, that the same sort of thing works for rectifiable sets. So you can likewise say that if you have a rectifiable, this is a theorem of Jones, that if you have a the analyst traveling salesman problem, which characterizes rectifiable sets in terms of sums like this, sums over many different scales and many different positions.
Another question. So is it correct that from this statement, quantitative statement, you get differentiability without using any coloring theorem?
No. So this is actually something I was going to talk about. So this was actually the next thing I was going to talk about. But no, because the thing is that what this tells you is that if you have a Lipschitz function, then you can find, and you pick a point, you can find infinitely many scales that get smaller and smaller, so that the function is getting closer and closer, is 1 over n differentiable at each of those scales. The trouble you have is that, well, what if, you know, you have a large scale where it looks like where the slope is something like that, and then a smaller scale where the slope goes the other way, and then a smaller scale where the slope goes the other way.
So the quantitative Rademacher does not imply Rademacher?
Not immediately. You can use these methods to eventually prove Rademacher, but it takes more work, because you need to figure out how to deal with situations like this, where at different scales it looks like a different affine function.
Thank you. More questions? I have more curiosity. So maybe you will talk about, do you have also a notion of epsilon rectifiability related to this epsilon?
Yeah, so this is like the beta numbers that Jones defines. Is the corresponding notion for rectifiability. Is basically, you know, you have a set which is close to a plane, is epsilon close to a plane, and then you want to, yeah, you want to quantify how often is this rectifiable set epsilon close to a plane.
But this notion of epsilon differentiability was already known, or was it pretty new?
I mean, this is essentially so Jones was working back in the 70s, I think.
With this notion?
He was working with rectifiable sets. But Dorn Soro was working with Lipschitz functions.
And also epsilon Lipschitz.
Something very similar, yeah. Like I think maybe like an L2 notion of closeness rather than an L infinity notion.
Thank you. So if not, there are no more questions. So we thank Robert for the next. So welcome. The next lecture will be by Giorgio Stefani from the University of Padua that will talk about user guide to distributional fractional spaces. Thank you.
Thank you, Valentino, for the introduction. Thanks to the organizer for the kind invitation, and thank you all for being here. So I will use my iPad and see if it will work till the end. The plan of the talk that I'm going to give is the following. This will be an introductory talk to the theory of distributional fractional Sobolev MBV spaces. So this is an introduction, okay? Introduction means no fine details, because maybe some of you are not familiar with fractional spaces and so on. So we'll try to give you the idea behind. The first part, 45 minutes, will be definitions. Then Sobolev, definition of Sobolev MBV, and some properties of this. The second part will be about the notion of perimeter. Then we move definition of the boundary. And from the boundary, we will go to definition and property of blow-up sets. Okay. So let me start with the first part. So we work in a Rham, n bigger or equal than 1. And the important parameter is alpha, which is the fractional parameter between 0 and 1. Okay. So the protagonist of this talk is the fractional gradient. So for a Lipschitz function with compass support in a Rham, so enough regular, say Lipschitz with compass support works, we define the fractional gradient of the function u at a point x as follows. So there is a constant in front, which we call mu and alpha, depending on the dimension and the parameter. And then we take an average on the full space, ui minus ux, y minus x, divided by y minus x to the power n plus alpha plus 1 dy. This is a vector, if it is well defined, because here I have points. Okay. This is a scalar, this is a vector. And similarly, if I have a function phi which is again Lipschitz from a Rham to a Rham, so it is vector value, the divergence of this vector field, same constant here, and here you take the same average but now with scalar product. Okay, so this will give you a number. Okay, the constant is not important for us. I will write it in any way, because as an exercise you can check the asymptotic behavior of this constant. So the idea is that when alpha is going to be 1, these operators will be the classical operator.
Okay, they are tending to the classical operator. Problem is that when alpha is going to 1, here you have, okay, this has order 1, so this will cancel this term here, and then you have n plus 1, which is not integrable, so you have to balance the explosion with something that is coming from the constant, and this can be checked. It is asymptotic, this is the volume of the unitary ball, to 1 minus alpha. So as alpha goes to 1, 1 minus alpha will go to 0. This is definition. Now question, is this a good definition? Yes. In fact, there are two ways. One way is to see, okay, just take the gradient, it's the same for the divergence. I bring the modulus inside in my definition, okay? So I put modulus everywhere. Apart from a constant, I will get this. Then I can integrate in x and get that the L1 norm of the fractional gradient is bounded by the so-called W alpha 1 semi-norm of the function u, which is this quantity here integrated in x. So if the function has this regularity, so the space W alpha 1 is very large, for example, Lipschitz functions are fine with comp support, then your operator is well defined, at least almost everywhere. Actually, you can split the gradient in two parts. So apart from constant, either you look to short range interaction, and there you can estimate this thing here with the Lipschitz constant. So you will get minus 1, and this is integrable, okay, close to the to point x, or use the fact that the function is bounded, so here you will get 2 times the L infinity norm of the function u divided by, and this will be integrable because you are far from the origin. So in particular, this will be always bounded by Lipschitz constant plus L infinity norm of u, okay, up to constant. And so we get that the alpha gradient for this function, Lipschitz with compass support, let's say, or Lipschitz unbounded, is an L infinity function. So in the end, it is, for this type of test function, it is an L1 and an L infinity function. So it is in all LP spaces. So why is this a fractional derivative of order alpha, let's say? Let me recall the definition of the Riesz potential. So for S between 0 and the dimension of the space, the Riesz potential applied to the function u at point x, which is the convolution of the kernel of the Riesz potential with the function u, I will use both the notations, is a constant integral u y divided by x minus y and minus s dy, zeta and s is still resembling the constant that I've written above. Okay. Here gamma is the gamma function as usual. Why I'm interested in this? Okay, let me remark this fact, which is the semigroup property. That is, if you compose with itself the Riesz transform, sorry, the Riesz potential, this I'm taking the convolution of the two, is and it, I will get the Riesz potential of order s plus t. This is the semigroup property. Okay, why I'm interested in so? Because the fractional gradient can be seen as the gradient, usual one, of the risk potential as an operator, okay? Or, because the two operators commute, the potential of the fractional gradient, which means if you want to take a derivative of order alpha, in this sense, which is the risk fractional derivative, first you differentiate one time, and then you integrate back of order 1 minus alpha, and you are left with the derivative of order alpha, okay? And the same story happens for the divergence. How do you prove that? Well, formally, okay, the two operators commute and it's fine. What we want to see is that one of the two coincides with the fractional gradient. So let's say that you take first the potential and then the gradient. Recall that by definition this is the convolution. I can move the gradient onto there is potential, okay? And then I have just to compute this gradient. So you do the computation. There is a constant here, which is the constant of the risk gradient. This is the risk potential, essentially. So I do the computation here, and what I come up is a constant which I can rewrite as, let me rewrite it as position divided by position to the power n plus alpha plus 1, which is the convolution operator that you find in the definition of the fractional gradient. And this one can check that this is precisely the constant that I have written in front. Let me go up 1 second. So here you have this convolution operator here. There is this ux that you have to get rid of, but when you are, let's say, far from the origin, then it is trivial that this integration will give you 0. Okay, so one do all the computation far from the origin and then pass to the limit. Okay. Proposition. So why I call fractional gradient and fractional divergence, are they related? Yes, there is an integration by part formula. If you take u times divergence alpha phi on the whole space, then you can move the divergence and get phi scalar nabla alpha u dx. Let's say for all sufficiently good function, for example, Lipschitz is fine, okay, as above. How do you prove that? Well, if I start from the left-hand side, for example, the divergence is the composition of potential and full divergence. Remember that this is a convolution operator, so by Fubini-Tonelli I can move it on u. And then I integrate by parts with the usual gradient. And again, I see that this is a fractional gradient. Okay. Of course, to do all the passages, I need some regularity. But once you have the regularity, which is enough to do the computation, you are done. And this regularity will work, for example. Now, we have gradient, divergence, integration by parts. So why not to define Sobolev space? So the weak gradient, weak formulation of the gradient, of a function u in LP over n for whatever p you want, 1 to infinity, is some L1 log function, vector valued, such that you have integration by parts in this fractional sense. For any test vector fields, even Lipschitz, that you like. Okay, this right-hand side is okay because this is compactly supported and smooth, and this is L1 log by definition. So this works fine. What about the right-hand side? Well, I said that if you take a good function, then divergence is in L1, cap and L infinity, while you assume that this function is in LP. Okay, so this makes sense. The integral is well defined. So, definition. This is the fractional, for me, the fractional distributionally defined Sobolev space. So, for P, whatever you like, define the Sobolev space as alpha P on the whole space Rn of function in LP such that the weak fractional gradient exists and it is an LP function. Okay. We arrived to this definition. Now the question is, what is this space? Is this linked to something that we already know? To answer this question, we have to formulate this space in a different way. So let me recall the following definition, which is the one of the fractional Laplacian. So we have alpha between 0 and 1, and u, say again, any sufficiently good function. The fractional Laplacian of u at the point x is a constant, different one, say, let's call it nu and alpha, integral on the whole space. Now you take uy minus ux divided by y minus x n plus alpha dy. Note that this is a different operator because we don't have the y minus x factor and the plus 1 below. So this is a number in principle. This constant here can be seen as the constant that I call it z, the one in front of the risk potential, of order minus alpha. Okay. This operator is well defined, at least for this function with this regularity. The important thing to keep in mind is the fundamental solution. Note that the Laplacian is an operator of order 2, derivative square. Then you are taking power alpha over 2. So this is formally an operator of order alpha. Okay. The fractional Laplacian of order alpha of the Riesz potential of order alpha is the Dirac delta. As operators, which means that the Riesz potential of order alpha is the fundamental solution of the fractional Laplacian. Okay, let's say on S distribution, so on C infinity C function. Okay. How do you prove that? Well, this is a good exercise with Fourier transform. So I will just sketch it, but you can check that the Fourier transform of the product of these two operators, since it can be seen a convolution, okay, then you get the product of the two Fourier transform, which you can compute, and the two are modulus to power alpha times modulus to power minus alpha. And then you get 1, which is the Fourier transform of the Dirac delta. This is formal, okay, because one has to check the fact that here you get some, say, some irregularity and so on. But if you believe me, this computation can be made rigorous. So one can see, one can understand the fractional Laplacian as the negative Riesz potential. Okay, remember the semi-group law. Okay. Any questions so far? Yes. Okay, at this level you can take it as a function here. This means that IS up to a constant is modulus to power S minus n. And this acts as a distribution on functions by convolution. Exactly. Everything can be seen either convolution of function, because you have all the regularity that you need. Take this definition for any, let's say, if I didn't write it, C infinity C or Lipschitz function will work for sure, because here you see at a point you have all the integrability you need, because it's n minus something. The problem is at infinity, but once you kill the problem at infinity, so on Schwarz function is completely fine, everything is well defined. Other questions? Okay. So, corollary. I would like to rewrite the fractional gradient in another way, trying to connect it to the fractional Laplacian. We have already seen that it's connected to the Riesz potential. Then I will write it like that. It is a gradient of order 0 combined with, applied after or before, doesn't matter because the two operator commutes, the fractional Laplacian. Remember that the fractional Laplacian is of order alpha, okay? So this has to be an operator of order 0. What is this magic operator of order 0? Well, without a lot of creativity, the fractional gradient of order 0 is the definition of the fractional gradient with alpha equal to 0. Which is a vector. Now, this thing here, if you say a Lipschitz compactly supported function, is almost fine. Why? Well, because if you bring the modulus inside, this one you kill, but then you get this power n, which is a problem because it's not integrable. Okay. So what you do is to say, okay, I have a problem here. What you do is to define this operator in a principal value sense. What does it mean? Up to the constant in front. So the correct definition is this one. I will take the limit as epsilon goes to 0 of Rn minus the problem of the same thing. This is now well defined because I'm integrating far from the singularity. Okay. Okay. This is the so-called principal value sense. Well, this, I'm saying that this definition is, if the limit exists, this is my definition, but the limit will exist because one can check that this operator is equal, up to the multiplicative constant in front, to the Riesz transform. This is what in literature is called the Riesz transform. And usually it is called R. Okay. What are the property of this operator once you define in a principal value sense as a distribution? Well, you can prove that if P is between 1 and infinity, then the Riesz transform as an operator take an LP function and map it into an LP vector value function. And actually it is invertible. If P is equal to 1, then this is not the case. You won't go in L1, you will go in the so-called L1 infinity or L weak 1. Okay, so these are larger space than L1 function. Okay. So this is good, this is bad. So for P bigger than 1 and less than infinity, I have something which is very good. Go back and forth from LP to LP. Now, how to prove this corollary? Again, by hands, I will tell you that I already told you that the gradient, the fractional gradient is the full gradient applied to 1 minus alpha. Then I can use the semi-group property. Here you see that I'm considering it as the negative potential, so it is the fractional Laplacian. And this, if you recall the definition of the risk potential, I'll go back 1 second. You can already see from the computation that we already done, because if you take the derivative of this with alpha equal to 0, then you get alpha equal to 0, alpha equal to 0, alpha equal to 0, and this is position divided by modulus, n to the power n plus 1, which is precisely what you get in the definition of the gradient 0. So believe me that you can show that this is the nabla 0. Remember that the risk potential is an operator of order S, if it is risk potential of order S. Okay, so this is a integration 1 time, differentiation 1 time, so I get operator of order 0. Okay, this is again formally, but can be made rigorous. Okay. This means that, so remember the definition of S alpha p. So S alpha p is LP function with a weak gradient in LP. But now, if I take the LP norm of the gradient, I can rewrite it as Riesz transform or gradient of order 0 of the fractional Laplacian applied to U. But this operator is continuous from LP to LP and invertible for P between 1 and infinity, which means that this can be controlled, so it's B-Lipschitz. Let's write me like that. This means B-Lipschitz, so you have a constant up and over and below, with the fractional Laplacian of U normal P. That is, the space S alpha P coincide with the space of function which are in LP and the fractional Laplacian is in LP. This is a well-known space, remember, for P between 1 and infinity. This is important. This is a well-known space. Usually it is written like that. And this is the so-called Bessel potential space. Well, the fractional Laplacian is not the Bessel potential. Why is this so? Well, usually via Fourier transform, let's say, but you can define it in many ways. The Bessel potential space in this fractional situation is defined via the Bessel potential. That is, you take any distribution and you ask that the Bessel potential, which is identity minus Laplacian to the power alpha over 2, is an LP function on Rn. But see, going in Fourier transform, what we are doing here is to apply the fractional Laplacian to the function u and asking, remember that this is a positive operator, and asking that it is an LP function, plus you add in the information that the identity applied to the function u is in LP, which means that the function u is in LP and the fractional Laplacian of u is in LP, which is precisely this. Okay. The identification between these two spaces is well known because it's simply realizing that this is the sum of two operators. Okay. What I'm interested in is to identify these two operators. And this is just because this gradient is the composition of fractional Laplacian and an operator of order 0, which is very good in this range of integrability regimes. They are exactly the same operator, and the space coincide. Other questions so far? Okay, so the conclusion, the answer to our question is this space here for p between 1 and infinity is a distributional definition of the Bessel potential space. And the Bessel potential space is very well known, very well studied, since probably the 70s, even before. So actually we didn't recover much. What I'm interested in is p equal to 1. P equal to infinity also is interesting, but I won't touch it. So what happens? For p equal to 1. Which is delicate. Yes? Okay, let me make this remark. So, for those who know, for p different from 2, let's say for p between 1 and infinity, which is the case I'm studying, for p different from 2, then the so-called space W alpha p on Rn is different from the space L alpha p, which is S alpha p. But you have some embeddings. That is, you can always prove that for p less than 2, you have this inclusion. Okay? So this space is larger in principle. While for p equal to 2, the two coincide. This is something magic that depends on the fact that both are Hilbert space. And when you're working with Hilbert spaces, then you can do some magic stuff with Fourier transform. For those who know, for those who do not know, let me define the space. This works for p between even 1, but not infinity. In that case, you have to take, of course, the modified definition. Is the space of function in LP such that the seminorm W alpha p is finite. What is this seminorm? Let me write power p. Well, this is the double integral on Rn of ux minus uy power p divided by y minus x and plus alpha p dy dx. Okay, So actually is the p power version of w alpha 1 that I recall you above. Any other questions so far? Yes?
For p greater than 2, we have an embedding.
Yeah, for p bigger than 2, you still have the embeddings. Let me write, For p bigger than 2, you still have the embeddings. You can always prove that you have the double inclusion. That is, if you ask for more differentiability, then you are inside the space. If you ask for less differentiability, then you are containing the space. Okay. So in some sense, they are not equivalent. So these are strict inclusion. But more or less, they are the same. Morally speaking, up to an epsilon, they are the same. But unfortunately, they are crucially different. Any other question? Yes?
P has a nice way to express it in Fourier transform terms.
W alpha p.
I don't know which one.
So this one can be expressed via Fourier transform, because this thing here, so essentially you rewrite this operator in Fourier transform. If you Fourier transform it, then you get something that is c to the power alpha, because I asked for alpha over 2, and you multiply this to the Fourier transform of u, because it's a convolution operator. For this one here, you don't have Fourier transform. Okay? Other questions? If not, I go back to my question. So what is happening for p equal to 1? Remember that in that case, the Riesz transform is very bad. In this case, you can touch measures. Okay. And when you touch measure, bad things happen. Or good things, depending on point of view. So for p, the definition is general. But for p between 1 and infinity, I would be interested in p equal to 1. But in any way, for p between alpha infinity and alpha between 0 and 1, we define the fractional variation of a function. So what we define is the fractional variation of the function u. U here is a function in LP. Okay. But now I'm interested in derivative in L1. So I will use the standard definition of VV function, so the standard definition of variation. So I will take the supremum of the integral of u against the divergence, in this case of the fractional 1, for C infinity C vector fields with norm less than 1, such that the support is contained in this open set omega. Okay? And omega is any open set in Rn, even Rn. Okay? But this is, I take an LP function, whatever, p between 1 and infinity. I am looking to the derivative of this function, and I will consider at first the fractional variation. This is the fractional variation of order alpha. In omega. And we define BV alpha p. Remember that we are taking fractional BV of LP function on omega as the space of LP function on Rn, such that the fractional variation of the function on omega is finite. If p is equal to 1, then it is simply BV alpha, okay? I won't repeat the 1. So be careful. I take an open set in Rham. I take an LP function on the whole space, and I take the fractional variation against test function with support in omega. Why I do so? Because, morally speaking, the definition of fractional gradient, the definition of the fractional gradient depends on the function on whole space. Okay, so I need to be defined everywhere, in principle.
So in principle, let's say that we change the definition of the fractional gradient and we restrict it to one of the set. Is it sensitive to the boundary, to the structure of the boundary of the open set?
If you restrict the integral, let's say, to an open set A, then what you need to know is what is the function in a neighborhood of A. Because if you want to compute it, you need to cross the boundary a little bit. For example, if you take a cutoff of the operator, instead of integrating on the full space, you just cut it off and you integrate just on an open set. But you need to move a little bit outside, say of size delta, if you truncate of size delta in your operator. Because you have non-locality, you always want to take an average. If you're still here, you would like to take at least an average on a ball of radius delta, and then you have to go a little bit outside.
Because it might explode because you don't have the cancelling of
Exactly. The problem is that you always want to exploit the fact that this thing here is 0, at least outside the ball centered at the origin of radius r. Bloop. So one can apply the Riesz transform, the Riesz representation theorem and discover that for an LP function on Rn, U is in BV alpha P of omega, if and only if there exists a measure a Radon measure vector value 1, which is finite, which is the fractional variation, such that you can integrate by part with respect to this measure. Okay, for every rest phi, vector valued, with support in omega. Okay, this is nothing but Riesz representation theorem. Analogously, one can define BV alpha P locally on omega. You again take function in LP of the whole space, but instead you ask that the fractional variation is finite on any open set compactly contained in omega. Okay, as usual. And in this case, you will get a measure, but this measure is not finite, is locally finite. But remember that we are always taking function on the whole space. And now the question is, what is BV alpha P, what are BV functions, what are BV sets. To answer this question, we need some additional information about our operators. So, let me add some properties. So the first thing is that the basic properties were proved by C. Lavi. I believe that the preprint is 2018, is the following. It is an invariant operator with respect to isometries. Of the space. Roto translation. That is, if you take the gradient of a translated function, then it is enough to take the gradient of the function and translate it. Where translation of a function means that you take fy plus x. Okay. If you instead rotate the domain and then you take the derivative, then essentially you do first the derivative and then rotate the vector. And these two are exactly like the fractional, the usual gradient. And the second thing is that it is homogeneous. Of order alpha. What I mean? If I take the derivative of the function u of lambda something, then this is lambda to the power alpha of the gradient of the function u lambda something. Okay, for every lambda positive. So basically we can rotate, translate for free and delete, but we have to pay a factor of power alpha. I will need the Leibniz rule. What I mean by Leibniz rule is the product rule. Remember that if you have the gradient of a product, then what you do? Derivative of the first times the second plus the first times the derivative of the second. Is this the same story here? No. You have to pay the non-locality. You can compute for at least, say, test function or Lipschitz with compact support, take the product, you work out the definition, and yes, you have something that resembles the local product rule. So this is the local part of the formula, plus there is a non-local remainder. Non-local NL, which depends on both U and V. What is that? Well, one can compute it out, and it is same old constant, integral whole space, uy minus ux, vy minus vx, y minus x divided by old friend y minus x power n plus alpha plus 1 dy. which is again a vector, okay? This is scalar, scalar, vector. And it is bilinear because, I mean, linearity, linearity, and it is also symmetric. With a simple estimate that one can prove is that if you take an L1, the L1 norm of this non-local part of the formula, then up to constant, it is the L infinity norm of one function, say V, times the semi-norm W alpha 1 of the other function. Simply because you bring the modulus inside, here you get modulus, here you get modulus, this thing here is 2 normal infinity, this goes away with that, and you get the semi-norm. Okay, small exercise. Proposition. Now remember the definition of fractional variation. You can prove that if, let's say, UK is converging to U almost everywhere in Rn, and the supremum, the essential supremum of the UK is an LP function, or UK is converging to U in a stronger sense, says in LP, for some P between 1 and infinity, then the fractional variation is lower semi-continuous, okay? And also you have the weak convergence in the sense of measure of the fractional variation measures, okay? Well, let's see the proof, just a sketch of it. How do you do? Well, take the distributional definition. Well, pointwise convergence, dominated convergence, or strong convergence in LP, you can write this as the limit of the UK. Then you integrate by part, and what you get is L infinity norm of the test times the fractional variation of U. And then you take the supremum with respect to phi of the first element. Okay. And the weak convergence is the same, is the same story. Another important fact that you can prove in this contest is the approximation let's say by test function. So any BV function, fractional 1, let's say p equal to 1 for simplicity, but you can prove it for p bigger than 1 also. Not for all p, but for some, yes. There exists a sequence of C infinity function, C infinity C function, such that two things. Of course, you converge strongly with respect to the L1 norm, because in this case I'm taking p equal to 1, sk goes to plus infinity, and you converge in energy. That is the total variation is converging to the total variation. Of course, you cannot have strong convergence of variation, because this is false even for alpha equal to 1. But you can prove the approximation. I will not detail the proof, but it is in two steps. Step 1, approximate BV alpha with BV alpha smooth. That is, how to do that? Take convolution with smoothing kernel. Step 2, use truncation. That is, multiply by a cutoff on BV alpha cap C infinity. Okay. To do that, you need convolution, but the operators are linear, so everything is fine. Truncation, so you multiply by a cutoff. You would like to know what happens to the product, but we have the product rule, and you have to estimate the remainder term, the non-local part, which is the one which is always a mess. Okay. Yeah, because I believe that Ancelotti Giaquinta is, this is Myers herring essentially. If you want to arrive to compact support, you need to add, say, truncation, that is, multiply. Exactly. You can do also for even for S alpha p, for every p. The story is the same. You have just to work in LP. Okay. Something that is fun is the fractional analog of the fundamental theorem of calculus. So the fractional fundamental theorem of calculus that tells you that uy minus ux can be recovered as the constant that I have written before, but with minus alpha, but it's a multiplicative constant that we really don't care for the moment. And here you have a big integral times the gradient. This is a z. Okay, dz. For every x and y in Rn, and let's say for every C infinity C function, for example. This is a fundamental theorem of calculus because you recover the function from the gradient. So once you know the gradient, you know the difference of the function at 2 points. You can prove that because in some sense, so the proof is based on, it's a little bit technical, but it's based on the fact that this you can play with the Fourier transform for that. If you take the divergence, instead of order alpha, you change and take the divergence of order minus alpha, so you put a minus alpha everywhere, and you apply it to the fractional gradient, then this, morally, is the divergence of 1 minus alpha, no, I changed the sign, it's 1 plus alpha, of gradient of order 1, of the risk potential of order 1 minus alpha. The plus and minus alpha goes away, you get divergence of the gradient, which means Laplacian, of I2. And I2 is the fundamental solution of the Laplacian. I alpha is the fundamental solution of Laplacian of alpha over 2. With alpha equal to 2, you get Laplacian. Okay? You work out this identity, and you go back to the formula that I've written before. It's a little bit technical. You have to apply approximation, so you reduce to C infinity C function, and then you apply this technique, this trick. Okay? There is also compactness once you get this. If you have a sequence of BV alpha function, remember p is equal to 1, just for convenience, such that the L1 norm plus the total variation is uniformly bounded, then there exists a subsequence converging to a limit function which is again in BV alpha by lower semi-continuity, converging in L1 lock. I cannot get anything more than L1 lock, even for alpha equal to 1, because you can take a ball and translate it to the infinity. You don't get L1. Okay? How do you prove that? Well, essentially the proof is based on this. Once you get the fundamental theorem of calculus, you understand that the translation of the function minus the translated function minus the function at a point is controlled by the gradient times something that is a constant coming from this bed operator. So from the fundamental theorem of fractional calculus, you can prove by integration that if you translate your function, say of h, and you integrate back minus the function, this is controlled by the intensity of the translation to the power alpha times the total variation. And once you get this, then you automatically get compactness by standard argument involving Fresh-Kolmogorov compactness theorem, because you control translation of the function. Okay, you already uniformly contouring L1. So this is the key point. Now we like to go back to the original question and move to at least two sets. So we say that a set, a measurable set, E in Rn as locally finite, fractional, Cacciopoli perimeter if the characteristic function of E is as fractional variation. Locally means that I will put a lock here, possibly. L infinity, so it is a characteristic function, so it is an L infinity function. So it is a BV alpha infinity function over n. If it is finite fractional Cacciopoli perimeter in omega, then it will be BV alpha infinity log of omega. Of course, characteristic function are in L infinity. Notation, we write perimeter of E in an open set A as the variation of the characteristic function, fractional variation, on A. And so perimeter alpha of E will be the total perimeter of E. This is not, is as not to be confused with the standard fractional perimeter, which may be I will decode P alpha, which is the one coming from the W alpha 1 setting, which can be written as you take the complement of alpha times, A complement times A complement, for example, if you take it in Rn, so you write here Rn, then empty set times empty set complement is Rn times Rn, and you get the W alpha semi-norm, W alpha 1 semi-norm of the characteristic function. Remember that this is not what I'm interested in. It's a different definition. Okay? And one can prove that my definition is more general. That is, the distributionally defined fractional perimeter of a set inside an open set is controlled. Actually, you can say what is the constant. It's our old friend mu n alpha times the standard fractional perimeter. This inequality can be strict. So the two are not equal. Okay.
So then, in case if both quantities are defined, can it be equivalent?
So you say if this is well defined, is it this well defined? Yes. If this is well defined, are these two equal? In general, no. We have example for which this thing is bigger than this thing here. Maybe they are equal with a different constant. No, this is not possible. Are they equivalent? We don't know. Question is it true that you have also, this is a difficult question for us. Is it true that if this is finite, if the smaller one is finite, then the bigger one is finite too? This will mean that the two perimeters are equivalent in some sense, point-wise, morally. We don't know. Example, before examples, another definition, which is the important one. So I said perimeter, I move to boundary, and then I move to blow up. Maybe I will need some, say, 5 extra minutes. Yeah, okay. Yeah, okay. Maybe some 5 extra minutes because of question. But anyway, the crucial definition is the fractional reduced boundary. So remember that our definition is distributional. So one idea is that you go back to the Giorgi, essentially, definition of fractional reduced boundary, and you apply it here in this context. So given E in Rn, with, let's say, finite perimeter, distributional one, inside an open set omega, define the fractional reduced boundary in this way. We say that X is in the reduced boundary, the fractional one, so letter is F, like frontier, okay? Inside omega, because these are the points in which my variation is finite, if and only if this is the definition, okay? The variation has to see the point. So basic stuff is that this point is in the support of the variation measure. Okay. Second thing, the limit I'm going to write exists, and I call it nu I alpha at x, which is the limit as r goes to 0 as the variation on the ball divided by total variation on the ball. And this is a unitary vector, unit vector, okay? This is what we call fractional inner normal. Just by definition, if you know that the fractional perimeter is finite, then you can integrate by part. And what you get is phi times the normal, the variation, which is a measure, and here you get the intersection with between omega and the fractional reduced boundary. This holds for phi, let's say, C infinity C, compactly supported in omega. Okay. So you can integrate by part and interpret this as a boundary. You can interpret it as a boundary, but it is not in general. Say you take the ball. Then, by definition, the fractional reduced boundary of the ball, what it is? Well, it is the whole space minus the center. And the normal, the fractional one, computed at a point x in the fractional reduced boundary, is the extension, the natural one, of the one of the ball. So it's very large. For the Hull space, let's say H centered at x0 direction nu, which means take points, say direction which is, say, unitary one, then the fractional reduced boundary of this set is the whole space and the fractional unit normal is the unit normal of the Hull space. Why? Why is this so? Why is BV, say, why is this boundary big or diffused? Because BV function, usual ones, are contained in W alpha 1 functions strictly, and W alpha 1 functions are strictly contained in BV alpha. remember that for this function here, we already see, we have already seen that this thing here is an L1 function. So, from the fractional point of view, BV functions are super regular. So even if it is something that jumps, from the fractional point of view, it's something that is smooth. Because you are looking to alpha derivative, not one. Okay? So this is normal. Once you want to play with non-locality, you have to accept that. Okay. So I would like to state yes. What identity? This one here?
No, the remark.
The remark? Yeah. No, actually it's trivial because it is a consequence of the definition. Let me write in a different color. This thing here is a characteristic function of E divergence alpha phi on Rn. You know that K of E is in BV alpha infinity loc omega. Okay. By Riesz representation theorem, I know that this is Rn phi integrated with respect to the fractional variation measure. But the definition that I told you tells you that on the support of the measure, remember that this integration is just on omega because phi is supported on omega. On that point, so you are on the support of the measure, that is what you care. On the support of the measure, you know that you are integrating on this boundary here, and on that boundary here you have defined the vector decomposition of the measure, that is exactly, this is the Radon-Nikodym definition.
But yeah, we are restricting ourselves to the case, I mean, to nu with not one, which is
exactly. But this is precisely the definition of this.
yes, no, yes, but
You say maybe this one.
this identity would be true with, I mean, the old density.
Ah, okay. Because I mean, you say you are imposing this this thing here. Well, yes, but I mean, I just care about normal. I mean, something that allows me to define a normal vector. So something that is unitary. Exactly. Otherwise,
Let's take a square in the plane. The limit exists, but it's not.
No, I know it. I know it. I mean, I know it can be different from one, but the point is, I mean, there is a bit of work to.
Exactly. I mean, it's not trivial, but it's based on first on Riesz representation theorem that allows you to write that, and then you work out the definition of fractional reduced boundary from here. This is not trivial, of course. Yes. I mean, passing from here to here, it pass from this definition here. Okay.
It's like the usual theorem.
Exactly. The Giorgio definition, actually. Okay, what was what I was saying? Okay, theorem. The target of my talk is to justify this theorem. I won't prove it, but I would like to convey the idea that it is possible to reach this result with what I have presented to you, working out the details. Okay. Working out the details a lot, but the main ideas are all in the presentation. So, let me give you first a definition, which is just a notation. The set of all tangent sets to a set E at the point X is the family of all N1 lock limits in a Rn of the rescale set. So you take your point, you move it to the origin, and you divide it by R, and you let R go to 0. So what is happening is that you are looking to your set at the point X, and you are zooming in and see what is happening in the limit. So first point, so let take a set with locally finite fractional Cacciopoli perimeter. Then 1, if you blow up on a point which is on the fractional reduced boundary, then you see something. There should be something. You are converging at least on one subsequence of radius going to 1, going to 0. You are converging L1 lock to something. 2. Remember that I have lower semi-continuity of variation, so these limit points must be of locally finite perimeter, again in the fractional sense, by lower semi-continuity of the variation. Second thing is that if you take any blow-up set, then you can compute the unit normal, the fractional one of this set, and this is equal to the fractional unit normal of the set E at the point X for almost every point with respect to the perimeter measure of the blow-up, say y, point y, in the fractional reduced boundary of F. One can say something more. This is contained in a paper by myself and Giovanni Comi, our first paper, distributional approach to fractional Sobolev NBV spaces, existence of blow-up. But you can say something more, and this you can work out with all the ingredients that I told you. I will tell you in moment some details, if maybe not, but the scheme is the following. To prove that you get something in the limit, you need some compactness. So you want to prove that you have some limit object, but we have a compactness result that has to be applied to characteristic functions. Okay? You don't have finiteness of the full semi-norm, but you can localize it, exploiting the fact that you are using characteristic function. So you get the existence of something. To characterize the existence of something, you have to do a careful analysis of the density of the measure at the point X. of the variation measure. And this will require some estimates that are based on the Leibniz rule. And that's it. You don't need anything more. You can work a little bit more and this is contained in Stefani, probably the last paper, which I believe is 2024, 2023, don't know what the year it was published, let's say 3, 4. So you require some 5 years of thinking. It was not difficult in the end, because when you've done it, you say, okay, it was fine. But you can say something more, and what you can say is the following. If, remember, you can translate and you can rotate. So we can assume that x is equal to 0, so I move my point of interest to the origin, and then I rotate my set E in such a way that the normal at x, which is 0 in this case, is the nth coordinate vector, unit vector. If F is a blow-up set, then F can be written in this way. It's an Rn minus 1 times a set M with M a set in R, which is a profile set, such that, and you can squeeze these 4, say 3.5 properties. Of course, the set has to have the same regularity you are working with. So it is a locally finite fractional perimeter set in R. And if you compute the fractional derivative of this characteristic function, so the total, the variation measure in R, so which is, let me write like that, so it's you are taking this, which is in R. Remember that M is a set in R. So let me write derivative one-dimensional of order alpha of this set, which is a measure on R. Well, this is a non-negative measure. So when you test against a positive function, it gives you a positive number, non-negative number. 2. This set has to be of full measure or zero measure. So it means that either the set or the complement has full measure. 3. If the set has full measure, otherwise apply it to the complement, then you look at it as a subset of the line, and you would like to know if it is spanning to plus infinity in an essential way. So the essential supremum, meaning that there is no place for which the set stops apart from negligible sets, meaning that the essential supremum of the set is plus infinity. And 4, which I would say is 3.5, is that if the profile set is not trivial, that is, is not empty or not R, which may happen. Think, for example, of the ball. If you stay far from the origin, then you blow up. Either you get the full space or the empty set. And I have to assume it. The integer perimeter of M is finite. Then the set M is an half line. And this point can be anywhere on the line. Question, is it the origin? One would like to know that. But remember that I am assuming this additional regularity, which is not granted at all. But if it happens that, then it is forced to be a line. In general, it is not. So I don't have time to explain the second part. For the first part, I told you, the first point is compactness argument. The second point is estimates on the size of the measure on balls centered at the point. And for that estimates, these density estimates, you need Leibniz rules, cutoffs, and so on. It's a little bit technical, but the essential points are here. If I can use 2 minutes, I will give you a list of questions. Because without questions, I mean, is there something else that you can do? So open problems for us. If you are interested in this type of matter, and you have some idea, please let me know. Okay, so what is R? I have never said that blow-ups are unique. Probably they are not. Think, for example, of the von Koch star or the von Koch shape. If you can blow up and you still get the von Koch or something else, still resembling the von Koch. At two different sequence of scales, you get something different. Okay, so it may happen that the blow-ups is not unique. So can you add some additional property? Or can you remove this assumption and prove that it is in any case an half line? Note that it cannot be, the blow up is never a cone because of this, okay? Unless it is an half space. We know that in the usual setting, blow ups are unique and are half spaces. In the fractional setting, we at least know that they are not cones unless they are empty, full space, or half space, okay? Because this force no cones. Second, I already told you that W alpha 1 is strictly contained in BV alpha, and it is strictly contained, but at the level of function. What does it mean? Problem. Is there a set which is here but not here? I know that there are functions in BV alpha which are not W alpha 1, but I don't know if there are characteristic functions in BV alpha which are not W alpha 1, which is connected to the question that it was posed before, that is W alpha 1 perimeter, if W alpha 1 perimeter is finite, then BV alpha perimeter is finite. But is it true that BV alpha perimeter finite, then also W alpha 1 perimeter is finite? That we don't know. So we, for the moment, have a different way of looking to W alpha 1 sets. Is there a purely BV alpha 1 set? So this is question number 2. In question number 3, you can prove, and this is last question and I will stop, you can prove that BV alpha is embedded in some LSP space there is a Sobolev embedding, and the correct exponent, you guess, it is this one, because you have to replace the 1 with the n divided by n minus 1. The 1 has to be replaced by alpha. This is true for all n bigger or equal than 2. Unfortunately, n equal to 1 is false. We have counterexample. So there is no embedding for n equal to 1. So there is, from this you get a Poincaré-Sobolev inequality that is a isoperimetric inequality. That is, the correct power of the volume is controlled by the perimeter fractional sense for any E in Rn. Take n bigger or equal than 2 for simplicity. Question, problem. What is the optimal constant? So what are the isoperimetric set? Are balls isoperimetric sets? We don't know. Why? The first thing that you would like to understand is if you can do a rearrangement. It is a decreasing rearrangement or something like that. If I go back, I will stop writing now. If I go back to the definition of this operator, remember that we are considering this operator here, and we are considering the L1 norm of this operator. Okay, so we are taking the modulus of this integral and then integrate another time in x. If you do rearrangements, you have to prove that in some way this product is decreased inside this integral by rearrangement. This is not clear at all, because here you have a sign, and this sign is not under control in a rearrangement. Okay? Because rearrangement works very well when you have the modulus, and in fact we know that optimizer for the fractional, standard fractional isoperimetric inequality in W alpha 1 are balls. But we do not know if you keep the modulus outside. Okay? And then I will stop here, and thank you very much for your attention and for your patience.
Thank you very much. Very nice lecture. Questions? Comments?
So, who is the first?
So a square does not finite fractional perimeter.
Yes, it has, because it is a BV function.
And the angles?
And the angles are not in the fractional reduced boundary. You can prove the following thing, that is, if you are in BV, then the essential part of the fractional reduced boundary, that is, avoid points in which a blow-up is trivial, Rn or the empty set, coincides with the reduced boundary of the Giorgi. So what you are adding for BV functions is simply places in which the set is stupidly optimal. That is, the blow-up, either you are in the interior or in the exterior. So for BV sets, we know everything about the fractional reduced boundary. And it is still proved after this blow-up result in this paper here. Sorry. Here you prove that BV sets, for BV set, the essential part of the fractional reduced boundary is the Giorgi. Even for locally finite perimeter. Okay. Who is second? Valentino.
Please,
Yeah, strictly bigger. It is in some W alpha 1 for some alpha, and so it is in some BV alpha. And the alpha is probably log 2 over log 3, or log 3 over log 4. I don't remember. Wait a moment. But if you take one point in the boundary of the von Koch snowflake, which is stable, that is, you are not splitting it anymore, then that is not in the fractional reduced boundary. Why? Because if you blow up along some scale, you get a blow up, which is again a von Koch set, and this is not of this form. So you are excluding the stable points. But nobody knows what's happening on the unstable points.
Do you construct an example of fractional offset with a fractional perimeter which has a singular part with respect to the back measure in the perimeter?
Yes, we have. For example, you can do this trick. You take a BV set, whatever you like. You apply the fractional Laplacian to this set of order 1 minus alpha divided by 2. This will give you a function, which is something that is going to explode at the boundary because the Laplacian will insert some singularity. And remember that the singularity it will give you is not something like that, it is something like that. You can compute the fractional gradient, the fractional variation of this thing, of this function. And for this function, you get that the fractional derivative is precisely the integer derivative of the characteristic function of the set. So you get something which is singular. If you would like to know a characteristic function, then we don't know. Because if you know that, then you have an example of a set which is not in W alpha 1, for which the gradient, the fractional gradient is in L1, so no singular part. And so you have the example that we are really looking for that. But you can construct function with this property. Problem is upper level set. Can you say something about upper level set? Because we don't even have a co-area formula, but it was too bad news for today. So.
Questions? Interesting questions?
Okay, no, maybe. When do we expect? Do we expect nabla alpha these operators to have local behaviors sometimes? Like I don't know, what are their? I mean, because they look pretty non-local.
They look pretty non-local, but you can do this trick, and which is something that we didn't discover ourselves. It was discovered by Schoenberger. He's a guy working in this kind of stuff. Now he's postdoc, I believe, in US. And he realized this thing that we generalized. As Andrea said, you can split the fractional variation, so nabla alpha, in something which is the absolute continuous part of the gradient, which is the one absolutely continuous with respect to the Lebesgue measure, plus the singular part. The singular part is local. And this is completely mind-blowing. That is, the non-locality is coming from the part which is absolutely continuous with the Lebesgue measure. So that is the part which is spreading the information all over the world. But what is really interesting from the BV point of view, that is the singular part, is local. To me, it's magic. And this magic, I don't understand.
This is the reason why, because at first it was not clear to me why we were expecting, I don't know, on the snowflakes to have interesting points at the actual boundary.
Exactly. The question is that it is, the point is that it is very difficult to take this quantity under control on a very difficult point on the snowflake. Because if your point is stable from an iteration and so on, then it will be something that is not in the fractional reduced boundary because of the blow-up theorem. So you have to look to something which is unstable, but to keep control of quantities on that kind of points is a mess, even in one dimension, not even in two dimensions. Just one dimension, it's very difficult. Take a Cantor set, fat Cantor set. Can you prove something? It's very hard. We are not able to do that for the moment. But if you come up with an idea in one dimension, please let me know.
More questions? We have still something.
Sure.
So does it make sense to hope for the Giorgio theorem here, kind of regularity of the reduced boundary?
Say you would like to say the fractional reduced boundary is the essential part, because remember the ball that in the case of the ball is full space minus the center. So you would like to remove the trivial part and see that it is truly a boundary. So we have proved something, that is, we know that if you look at it from the measured point of view, that is, you intersect with balls and you would like to know that the volume of balls, you can prove something and say that it is contained in the measured theoretic boundary of the sets, but this can be very large even for BV sets. So it is not just a topological boundary. If you would like to have some kind of rectifiability, that is, it is piecewise something, and then there is a ghost behind you, and that ghost is price. Because this type of operators will give you a measure which is absolutely continuing with respect to Hausdorff measure of order of dimension n minus alpha, with alpha non-integer. And if alpha is not integer, then the only possibility is that either it's something that is trivial, or it is hn, either it is n minus 1 or it is n from the dimensional point of view, if it is something that has density control from above and from below. So question is, can you detect this jump, or can you force this variation to see really dimension n minus 1 when you move to the essential part of the boundary? It is so if you are in the integer BV case. We already proved that. Question is, what can you say outside BV? So for more irregular sets. And that we don't know.
In the case of fractals, you could expect some older regularity.
Exactly, but then you need a older rectifiability theory. That is something that is worked by also Giacomo Del Nin. There is also Andrea. I mean, many people here that I won't mention because the list is very long. Also you, but also I'm interested from older, because if you are in the Sub-Riemannian world, then you know that rectifiability is older from the Euclidean point of view. This question was also posed to me many years ago by Bruno Franchi, and the question is maybe, but we don't have. I mean, unless you have some extra information on the blow up, I don't see how you can prove. I mean, you really have to understand what is this profile set. I mean, if it is something like that, even if without the finite perimeter assumption, then maybe you can say, okay, now I'm studying what is this M, and see what is this space. Maybe it's a null space, but it's just moved a little bit, or maybe it is something that can be approximated by, say, parabolas or whatever. Okay, but I mean, the problem here is with the blow up.
Thank you, Giorgio, for the very nice lecture.
Thank you.